What if the universe is hiding something faster than light, invisible to the eye, and capable of breaking the very flow of time? Deep within the shadows of particle physics lies a mystery no one can fully explain, the tachyonic neutrino. Long thought to be impossible, this theoretical particle could be the key to unlocking a hidden layer of reality. If it exists, nothing, time, space, or causality, will ever be the same again. But before we continue, subscribe to the channel so you don't miss out on any of these videos. You're about to fall into a rabbit hole deeper than most people even know exists. A realm where time might not flow in one direction, where mass can be imaginary, and where the most elusive particle in the universe might also be its most rebellious. For decades, physicists have speculated, what if neutrinos, the nearly massless particles that flood the universe by the trillions every second, are actually tachions? Not just fast, but faster than anything we've ever imagined. It sounds impossible. It feels like the kind of thing you'd hear in a late-night sci-fi movie. But buried within the mathematics of quantum field theory, special relativity, and the deepest corners of experimental physics lies a question no one has definitively answered. What if neutrinos can break the speed of light? What if tachyonic neutrinos are real? Before we even get into the heart of this mind-bending idea, let's step back and understand why it's so radical. Light speed, as Einstein taught us, is not just fast, it's the limit. The absolute cosmic speed limit. No matter how much energy you pump into a particle, if it has mass, it can never reach light speed. But tachions? They're not trying to reach it. They've already passed it. For them, slowing down to the speed of light would require infinite energy. In their world, light is too slow. So now, imagine what it means if neutrinos, the same ghostly particles we've observed in nuclear reactions, in the heart of the Sun, and from distant supernovae, turn out to be tachions. It would mean that every neutrino passing through your body right now, billions per second, might actually be moving backward in time from its own perspective. It would mean our universe, as we understand it, isn't just incomplete, it's fundamentally upside down. The first hints of this idea didn't come from wild speculation. They came from math. In certain interpretations of quantum field theory, solutions exist where particles could have imaginary mass. Not imaginary as in made up, but literally involving the square root of a negative number. Mathematically, this corresponds to something moving faster than light. And as weird as that sounds, the math doesn't forbid it. It's uncomfortable, but it's consistent. That's the thing about the universe. It doesn't care if something makes sense to us. It just is. Over the decades, physicists have gone back and forth on the idea of tachions. In some contexts, they're considered unphysical artifacts, just strange mathematical byproducts that we can safely ignore. But in other contexts, particularly when it comes to neutrinos, the possibility just won't go away. Every time we get better at measuring neutrinos, learning more about their oscillations, their tiny masses, and their strange ability to pass through matter like it's not even there, we find just enough mystery to keep the tachyonic question alive. In 2011, the scientific world was rocked when the Opera experiment in Italy announced it had detected neutrinos apparently traveling faster than light. The news sent shockwaves through the physics community. If true, it would have shattered one of the most fundamental principles of modern physics. Scientists around the world were skeptical, understandably. The results were eventually attributed to a faulty cable connection. An error. A mistake. But for a moment, the world glimpsed what it would feel like if tachyonic neutrinos were real. And that moment sparked something that still hasn't faded. Here's the thing, just because the Opera experiment was flawed doesn't mean the idea is dead. In fact, it's more alive than ever. Physicists are still probing the nature of neutrino mass with unprecedented precision. We've discovered that neutrinos oscillate between different flavors, electron, muon, and tau, as they travel. And this only happens if they have mass. But that mass is incredibly tiny, and the exact values are still elusive. Some theoretical models have proposed that the observed behavior of neutrinos could be consistent with a tachyonic mass term. In other words, neutrinos might not just be light, they might be faster than light. To understand how this could be possible, we have to dive into the very fabric of relativity. According to Einstein's equations, particles can be categorized based on their mass. Regular particles with positive mass, like electrons and protons, massless particles, like photons, and hypothetical particles with imaginary mass, tachyons. Regular particles accelerate toward the speed of light but can never reach it. Massless particles always travel at the speed of light. But tachyons would always travel faster than light. And they could never slow down to or below light speed. But what does it mean for something to have imaginary mass? In physics, mass isn't just a number. It's a fundamental property that affects how a particle moves, interacts, and even exists. When you introduce an imaginary mass into the equations of motion, everything changes. The energy-momentum relationship, the equation that links a particle's energy, momentum, and mass, becomes radically different. Instead of you get, where is the imaginary mass? This flips the entire structure of the physics we're used to. Now, if you imagine a neutrino with this kind of behavior, it means we might have to rethink how we observe the universe. Tachyonic neutrinos would affect the way we detect signals from supernovae, how we measure the early universe, and even how we interpret the arrow of time. They could, theoretically, send information into the past. They could break causality. Of course, this opens a whole can of worms. If you can send a signal faster than light, then you can send it into the past, depending on your frame of reference. That means you could, in theory, create paradoxes, change the outcome of events that already happened. This is one of the biggest reasons physicists are hesitant to accept tachyons as physical reality. The universe seems to have a built-in resistance to causality violations. But does that mean tachyonic particles are impossible? Or just that we haven't figured out how they fit in yet? Even if we set aside causality for a moment, there are still practical implications. The existence of tachyonic neutrinos would alter how we understand neutrino detection experiments. It could change the way we interpret results from the ice cube experiment in Antarctica, or from super cameo candy in Japan. It would require rethinking how neutrinos interact with other particles, how they contribute to the mass-energy content of the universe, and how they influence cosmic evolution. And we're just scratching the surface. Because tachyons aren't just a curiosity, they could be the missing link in understanding dark energy, quantum gravity, and the unification of forces. They might be the clue that connects string theory with observable physics. They might even be responsible for phenomena we haven't yet attributed to any known particle. As strange as it sounds, some models of tachyonic neutrinos propose that these particles don't violate causality at all. Because their interactions are so limited, they can't actually be used to send usable information faster than light. They might move faster than light in terms of phase velocity, but not in terms of signal velocity. It's subtle, but crucial. This would mean we get all the weirdness of tachyonic physics, without breaking the rules of the universe. But there's a problem. We haven't seen definitive proof. We don't have clear, unambiguous experimental data showing that neutrinos are tachyons. And until we do, the theory remains speculative. Still, the mathematical frameworks that support it are robust. The questions it raises are compelling. And the potential consequences are too big to ignore. Let's start with what we know, and then slowly spiral into what we don't. Neutrinos. They're ghosts. Literally. These particles pass through your body by the trillions every second, without leaving a trace. You could be standing in front of the most powerful neutrino beam ever created, and you'd feel absolutely nothing. No heat. No force. Nothing. That's because neutrinos interact so weakly with matter that they can travel through entire planets, as though they weren't even there. In fact, that's exactly what they do. Now here's the kicker. For decades, scientists assumed neutrinos were massless. That made sense with our standard model of particle physics, our best, most precise attempt at understanding the fundamental components of the universe. But then came the observations. The anomalies. The hints that neutrinos were changing flavors as they moved, morphing from one type to another, like some shape-shifting quantum entity. And that could only happen if neutrinos had mass. Tiny, yes, but not zero. And with that realization, everything changed. If neutrinos had mass, even a minuscule amount, that meant the standard model was incomplete. It wasn't wrong per se, but it was lacking. Suddenly, the door was opened to an entire world of new physics, and it didn't take long for people to start asking the real questions. Not just, how much do neutrinos weigh? But, what if their mass is different? What if it's not just small, but imaginary? This is where things get strange. In physics, imaginary mass doesn't mean not real. It means a mass term involving the square root of a negative number. You've probably encountered imaginary numbers in school, numbers like I, where I superscript 2 equals -1. It's a mathematical tool, but when applied to mass and relativistic equations, it predicts something wild, a particle that always moves faster than light. That's what a tachyon is. A theoretical particle with imaginary mass that cannot slow down below light speed. It's locked into the superluminal regime, like a fish stuck on the far side of a cosmic current. According to special relativity, normal particles with real mass can never accelerate to light speed. It would take infinite energy. But tachyons? They're already beyond it. And to slow down to light speed would require infinite energy. They live on the other side. Now, combine that with neutrinos. Particles we barely understand, but which already exhibit behavior that seems quantumly bizarre. If neutrinos are tachyons, tachionic neutrinos, then the implications are so deep, so vast, that we need to reframe our understanding of time, causality, energy, and the very structure of the universe. But why even consider it? Why do some scientists entertain the idea that neutrinos might be tachyons? The answer lies in anomalies. In data. In those little whispers of the universe saying, "Hey, something doesn't quite add up here." In 2011, an experiment called Opera, based in Italy, sent neutrinos from CERN in Switzerland to a detector 730 kilometers away. The neutrinos arrived a few billionths of a second earlier than light would have, given the same distance. It was a tiny discrepancy, but if accurate, it would have shattered Einstein's postulate that nothing can move faster than light. The scientific community erupted. It was front-page news. Had we found a loophole in relativity? A crack in the wall? But then came the reanalysis. A loose fiber optic cable. A timing error. The superluminal result was retracted. It wasn't real. Or was it? Some physicists weren't convinced that all the anomalies were errors. There had been other strange results over the years, less publicized, less dramatic, but still curious. A few scattered studies had hinted that neutrinos might not be behaving entirely as expected. Their masses seemed to shift. Their speeds, in some cases, might exceed what should be possible. Most of these results were within margins of error, but the pattern was enough to provoke a question: what if we're missing something fundamental? And that brings us to the mathematics, the realm where possibility isn't restricted by what's been measured, but instead by what's been imagined. The Klein-Gordon equation is a relativistic generalization of the Schrödinger equation. When applied to a particle with imaginary mass, it yields solutions consistent with superluminal propagation. In quantum field theory, it's entirely possible to define a field with tachyonic mass, a field whose lowest energy state occurs not at zero, but at some non-zero value. This idea actually appears in the Higgs mechanism. The Higgs boson arises from a tachyonic mass term in the Higgs field, which leads to spontaneous symmetry breaking. In other words, tachyons aren't just fantasy. They're already in our equations. We just don't know if any real, propagating particle fits the description. Enter the neutrino. If neutrinos are tachyons, then we need to redefine how we talk about mass. Instead of saying they have an imaginary mass in the everyday sense, we say they have a negative mass squared. This isn't just wordplay. Experiments that attempt to measure the neutrino mass, such as those studying tritium beta decay, sometimes yield results consistent with a negative mass squared value. Not always. Not conclusively. But enough to keep the idea alive. It's like a ghost on the edge of the data, never fully materializing, but never entirely going away either. And if this ghost is real, it means time itself becomes a slippery concept. You see, tachyons break causality. That's the scary part. If something moves faster than light, it can, in certain reference frames, arrive at a destination before it even left. It's not just counterintuitive. It's universe breaking. It means effects could precede causes. It means the arrow of time could bend back on itself. It means your future self could send a message to your past self. For physicists, this isn't just an academic concern. It's a crisis. The entire framework of physics is built on cause and effect. Break that, and you unravel everything. So, are tachyonic neutrinos real? Or are they a beautiful illusion, conjured by mathematical artifacts and experimental noise? The truth is, we don't know. But let's not stop at we don't know. Let's explore every angle, every test, every wild idea that's ever been proposed around this concept. Because if there's even a chance that neutrinos are tachyons, then we're standing at the edge of the biggest scientific revolution since Einstein scribbled on a notepad in 1905. In mathematics, imaginary numbers are perfectly valid and extremely useful, but in physics, attaching an imaginary value to something as fundamental as mass gets complicated. Mass determines how an object behaves under the influence of forces, how it moves through space-time, and crucially, how fast it can go. According to Einstein's theory of special relativity, anything with real, positive mass cannot reach the speed of light. It requires infinite energy to do so. Light itself, of course, travels at light speed precisely because its particles, photons, have no rest mass. But here's where things take a turn. If a particle had an imaginary mass, then the math of relativity doesn't break. It just flips. Instead of requiring infinite energy to reach the speed of light, it would require infinite energy to slow down to it. That's right, if a particle had imaginary mass, it would always be traveling faster than light. It would never go below that universal speed limit. This is the idea behind tachyons, hypothetical particles that inherently travel faster than light. And if neutrinos possess this quality, they would be tachyonic in nature. The mere possibility is enough to send ripples through every equation and theory in modern physics. It violates the comfortable causality we take for granted. It opens the door to effects preceding causes, to paradoxes that tangle timelines like knots. It whispers of time travel and reversed entropy, and the kind of quantum weirdness that keeps even the most seasoned physicists awake at night. The first serious buzz about superluminal neutrinos began in the early 2010s, with the Opera experiment. Scientists were sending neutrinos from CERN in Switzerland to the Gran Sasso lab in Italy, a distance of about 730 kilometers. The shock came when the neutrinos appeared to arrive slightly faster than light would have over the same distance. Not by much, just a few parts in 100,000, but enough to shake the very foundations of physics. Were these results real? Were neutrinos actually moving faster than light? The media exploded. Headlines proclaimed the end of Einstein's reign. Physicists around the world double-checked equations and measurements. The idea of tachyonic neutrinos moved from fringe theory into the spotlight. People speculated wildly. Were we seeing the first empirical evidence of tachyons? Was time about to lose its arrow? Of course, the thrill didn't last. It turned out to be a mistake, an error in the fiber optic timing system used in the experiment. Once corrected, the neutrinos' speeds fell back below the light barrier, just where we expected them to be. Most people moved on. But for a small subset of physicists, that moment sparked something deeper, a drive to reconsider what tachyonic mass really means, and whether neutrinos might still, under the right framework, fit the definition. Tachyonic fields containing particles with imaginary mass, aren't new to physics. In fact, they're used in theoretical contexts more than most people realize. The Higgs mechanism, the very process that gives particles their mass, begins with a kind of tachyonic mass term. It's not that the Higgs boson is a tachyon, it isn't, but rather that the instability in the Higgs field resembles the behavior of a tachyon until the field settles into a lower energy state, giving particles their mass. So the idea of imaginary mass is baked into some of our most successful theories. It's not forbidden. It's just unusual. So what would it mean if neutrinos were genuinely tachyonic? The consequences stretch far beyond just speed. It would change how we understand spacetime itself. In a world where tachions are real, every event becomes smeared across a wider canvas of cause and effect. Information might travel backward. Energy might not be confined to traditional limits. Even the structure of vacuum space could be affected, because tachyons don't obey normal quantum rules. They create instabilities, they demand new symmetries, and they challenge our notions of what a particle even is. Some researchers have explored tachyonic neutrinos as a way to explain dark energy, the mysterious force causing the universe to accelerate in its expansion. If a background sea of tachyonic neutrinos exists, their strange properties could interact with the fabric of spacetime in subtle, pervasive ways, pulling on it, warping it, nudging galaxies apart. Others have proposed that tachyonic neutrinos could be linked to the early universe, playing a role in the inflationary period that drove cosmic expansion in the first moments after the Big Bang. The mathematics of tachyonic neutrinos is rich and treacherous. You don't just plug in an imaginary mass and call it a day. You have to redefine how energy and momentum work. You have to grapple with negative energy states, with non-unitary evolution, with violations of Lorentz invariance, the foundational symmetry of special relativity. And perhaps most dangerously of all, you have to confront the specter of causality violations. If a particle can move faster than light, then in some reference frames, it appears to move backward in time. And if you can send information backward in time, even in principle, then paradoxes bloom like weeds. This doesn't mean the universe implodes. Physicists have developed frameworks, such as the reinterpretation principle, that avoid paradoxes by treating tachyons as always moving forward in their own causally consistent way. But it's a delicate balance, and not everyone agrees. The debates are fierce, the calculations intricate, and the implications staggering. Theoretical work continues. Models have been proposed where the neutrino field includes a tachyonic component. These models attempt to reconcile the observed neutrino oscillations with a more exotic mass structure, where at least one neutrino flavor has a negative mass-squared value. That's the key signature of a tachyon. In fact, some experimental results from tritium beta decay studies, most notably from the Mainz and Troitsk experiments, hinted at just that, a negative mass-squared result. Not enough to confirm anything, and well within the margin of error, but enough to keep the speculation alive. Then came the Cochrane experiment, the most sensitive neutrino mass measurement ever attempted. By studying the endpoint of tritium beta decay with unprecedented precision, Cochrane sought to measure the mass of the electron neutrino directly. And again, the results were not definitive. The neutrino mass appeared to be extremely small, possibly zero, but with error bars that just barely allowed for the possibility of a tachyonic value. Physicists around the world scrambled to replicate the results, or explain the anomaly. For a few electrifying months, the possibility of superluminal neutrinos wasn't just speculative, it was empirical. The equations were double-checked, the instruments recalibrated, and every alternative explanation was exhausted. But eventually, the truth emerged. The faster-than-light result was due to a loose fiber optic cable in the GPS system used to time the neutrino pulses. It was a mundane, even embarrassing error, but for a brief window, the world caught a glimpse of what it might feel like to watch physics rewrite itself in real time. Still, the idea refused to die. Why? Because even before the Opera experiment, and long after it, certain theoretical frameworks suggested that tachyonic neutrinos might not be such a wild idea after all. The concept didn't start with Opera, it only brought the conversation into the spotlight. Deep within quantum field theory, particularly in the Dirac equation and extensions of the Standard Model, neutrinos with imaginary mass had already been explored. Some theoretical papers even proposed that a tachyonic mass term could help resolve long-standing mysteries, such as the nature of dark energy or the origin of neutrino oscillations. To understand how this works, consider the mathematical machinery behind particles. In the Standard Model, mass is typically introduced via the Higgs mechanism. But the same formalism allows for mass terms that break certain symmetries, such as CPT symmetry, which combines charge conjugation, parity transformation, and time reversal. A tachyonic mass term would violate these symmetries in a very specific way, potentially opening up new routes for understanding why neutrinos behave so differently from other particles. And that difference is important. Neutrinos are unlike anything else we know. They're electrically neutral, incredibly light, and only interact via the weak nuclear force and gravity. This makes them almost invisible to detectors, but also incredibly valuable as messengers from the distant universe. They stream from the cores of stars, from supernovae, from black hole accretion disks. They even come from the Big Bang itself, forming what's called the cosmic neutrino background, an invisible relic of the universe's earliest moments. Now imagine that some or all of those neutrinos are tachyons. It changes everything. Because tachyons would interact differently with the fabric of spacetime itself. They could, theoretically, violate causality. That means you could detect a tachyon before it was even emitted. In a thought experiment, this would allow messages to be sent into the past. And while no practical mechanism for this exists, or may ever exist, the mathematics doesn't outright forbid it. The implications go far beyond faster-than-light travel. If neutrinos are tachyons, they might have a preferred reference frame, a kind of universal background against which all their motion is measured. This would violate Lorentz invariance, one of the cornerstones of relativity. And if Lorentz invariance is violated, then perhaps other fundamental assumptions of physics are also up for revision. We might need a new theory, beyond both quantum mechanics and general relativity, to describe the true behavior of nature at its deepest levels. But let's slow down for a moment. What would a tachyonic neutrino actually look like in an experiment? The answer is subtle. Tachyons, by definition, can't be brought to rest. So we can't isolate one in a lab and study it in the same way we study electrons or protons. But we can look for indirect evidence. One method is to examine the energy spectrum of beta decay, specifically in tritium, a radioactive isotope of hydrogen. In a normal decay, the electron and neutrino share the energy of the decay in a predictable pattern. But if the neutrino is a tachyon, the shape of that spectrum changes, especially near the endpoint, where the neutrino carries off very little energy. The Cochrane experiment in Germany is designed to measure this spectrum with exquisite precision. Its goal is to pin down the neutrino mass, or at least place strict limits on it. But tucked within those measurements is the potential to detect deviations, tiny hints that the neutrino might be something stranger than we imagined. A handful of theoretical papers have modeled how a tachyonic neutrino would modify the spectrum. And while Cochrane has yet to find any smoking gun, the data is still being refined, and future upgrades could improve sensitivity even further. Meanwhile, there's another angle to consider: cosmology. The early universe was a seething cauldron of particles and radiation, and neutrinos were right there at the beginning. If they're tachyons, they would have influenced the rate of expansion, the formation of structure, and the evolution of cosmic microwave background anisotropies. Researchers have already used cosmological data to constrain neutrino mass, but with new satellite missions like the James Webb Space Telescope and CMBS-4 coming online, we may be able to refine those constraints to the point of detecting, or excluding, tachyonic behavior. But here's the twist: even if neutrinos aren't tachyons now, they might have been tachyonic in the early universe. This leads us to another fascinating idea: phase transitions in mass. In some theoretical models, particles can undergo transitions in their properties as the universe cools. Just as water turns to ice at 0 degrees Celsius, certain fields may freeze out, locking particles into stable states. It's conceivable that neutrinos started out tachyonic and then acquired real mass later. This would leave imprints in the early universe, possibly detectable through gravitational waves or subtle features in galaxy clustering. The beauty of tachyonic neutrino theories lies in their ambition. They don't just try to explain one phenomenon, they aim to unify many. The origin of mass, the nature of time, the speed of information, the structure of spacetime itself. These theories often intersect with string theory, with loop quantum gravity, with ideas about extra dimensions and holographic universes. They're not just an answer to, how fast can a particle go? They're a gateway to, what is the universe really? Neutrinos are unlike any other known particles. They are incredibly light, millions of times lighter than even the electron, and they interact via only the weak nuclear force and gravity. No electromagnetic interaction, no strong nuclear force. This means they can pass through vast amounts of matter without leaving a trace. But more importantly, they come in three flavors: electron, muon, and tau, and they can oscillate between these flavors as they travel. This phenomenon, neutrino oscillation, is one of the few confirmed observations that requires neutrinos to have mass. But the kind of mass they possess has remained deeply mysterious. In conventional models, these masses are thought to be real and positive, just very, very small. However, in tachyonic neutrino theories, the suggestion is that these masses are not just small, but fundamentally different in nature, imaginary numbers that change the way neutrinos move through spacetime. This isn't just a mathematical curiosity. It has very real, physical implications. If neutrinos are tachyonic, they would always travel faster than light, and their apparent slowness in experiments would be an illusion caused by the way we detect and interpret their interactions. To wrap your mind around this, you have to let go of a deeply held assumption that faster-than-light motion is impossible. Special relativity forbids any particle with real mass from reaching or exceeding the speed of light, because doing so would require infinite energy. But that prohibition doesn't apply to particles that were born superluminal. In fact, relativity allows them, as long as they never slow down to or below light speed. These hypothetical particles, tachyons, would follow a different set of rules. Their energy decreases as their speed increases, and vice versa. The faster they go, the less energy they carry, in a bizarre reversal of our normal expectations. This behavior leads to an even stranger consequence. If tachyons could be detected and manipulated, it might be possible to send information backwards in time. Think about that. If a particle moves faster than light, and light represents the ultimate limit of causal influence, then a tachyon could, from some perspectives, arrive before it was sent. That alone throws the principle of causality into chaos. Cause would no longer precede effect. You could receive a message before anyone sends it. Paradoxes like the famous grandfather paradox become real possibilities in such a universe. But don't misunderstand. Tachyonic neutrinos don't necessarily mean you can build a time machine. The mathematics is more nuanced. In most models, tachyons can't be used to transmit usable information faster than light. Their behavior is governed by quantum uncertainty and probabilistic outcomes. Still, the possibility opens unsettling doors. One of the reasons this idea is so compelling is because of how well it slots into some of the deepest puzzles in cosmology. For example, consider dark energy, the mysterious force causing the universe to accelerate in its expansion. Some researchers have proposed that a background field of tachyonic particles, including neutrinos, could contribute to this accelerating force. Unlike ordinary matter or radiation, which dilute as the universe expands, a tachyonic field could exert a persistent pressure that drives the cosmos apart faster and faster. Even more intriguingly, there are hints that the observed distribution of neutrino masses and their oscillation behavior might better fit models that include a tachyonic component. It's not that the standard models don't work, it's that tachyonic versions might explain more with fewer assumptions. In physics, that's gold. Theories that provide more predictive power while requiring fewer arbitrary parameters are often the ones that make it through the brutal crucible of experimental verification. But let's pause and ask something deeper. What is mass, really? If we're even entertaining the idea that neutrinos have imaginary mass, it forces us to re-examine one of the most fundamental properties in physics. Mass isn't just how heavy something is. In Einstein's universe, it's deeply tied to energy, space-time, and the curvature of the cosmos itself. Real mass curves spacetime, draws other masses toward it, and anchors objects within a subliminal, light-speed limited framework. So what does imaginary mass do? If tachyons exist, they might not bend spacetime the way ordinary matter does. They could interact with the geometry of the universe in an inverted way, repelling instead of attracting, destabilizing instead of stabilizing. Some versions of tachyonic field theory predict that these particles could permeate the vacuum, creating instabilities or transitions between different vacuum states. This connects directly to theories like string theory, where tachyons are often seen not as particles per se, but as indicators that a given configuration of the universe is unstable and wants to shift into a more stable, lower energy state. In that view, tachyons are less like physical things and more like warnings, cosmic clues that the structure of reality is about to change. They herald phase transitions in the fabric of the vacuum itself, potentially rewriting the rules of physics as they go. And if neutrinos are tachyonic, it raises a fascinating question: are we living in a universe still in transition? This question takes us to the very edges of modern theoretical physics, into domains where quantum mechanics and general relativity intersect and clash. Consider this: the early universe, mere moments after the Big Bang, was a chaotic, boiling sea of particles and fields. As it cooled, it underwent multiple symmetry-breaking events, phase transitions that separated the forces of nature and allowed particles to acquire mass. If neutrinos are tachyonic, they could be relics of one such phase transition. They might be the only surviving evidence of an earlier, more symmetrical version of the universe. This would explain not only their peculiar mass, but their near invisibility, their ghost-like passage through matter, and even their role in cosmic evolution. In this sense, neutrinos could be messengers, not just from the distant reaches of space, but from an earlier, primordial state of reality itself. They are, quite literally, fossils from a deeper layer of existence. Even more radical ideas have been proposed. In some speculative models, tachyonic neutrinos are linked to the multiverse, the notion that our universe is just one of many. Because tachyons can exist outside the usual constraints of time and space, they might be able to interact across multiple timelines or realities. They could be leaking in from neighboring universes, or slipping between them. Some even speculate that certain anomalies in neutrino detection, such as unexplained time shifts or energy spikes, might be evidence of this kind of interuniversal crossing. Now, let's turn to the realm of detection and experimentation. How could we know if neutrinos are tachyonic? What would we look for? Traditional experiments measure neutrino mass through their effects on beta decay, cosmic background radiation, and large-scale structure formation. But if the mass is imaginary, those effects might be hidden or inverted. One promising approach involves precision measurements of the endpoint of beta decay spectra, looking at the very tail end of electron energy distributions in specific decays. The Causality experiment in Germany is currently one of the world's leading efforts in this domain, aiming to pin down the neutrino mass with unprecedented accuracy. If the measurements yield a negative mass squared value, not just 0 or close to 0, but actually below 0, that would be a strong hint of tachyonic behavior. And in fact, some early data from previous experiments did show such hints, though they were within the margins of error. Still, these anomalies have kept the door open for theorists to speculate, and for experimentalists to keep pushing the boundaries. In fact, the detection of tachyonic neutrinos could revolutionize our understanding of fundamental physics. But there's a catch. The very nature of these particles means they might evade detection by traditional means. Since tachyons would always travel faster than light, they could potentially outpace the detectors themselves. This creates a dilemma for physicists. How can you measure a particle that doesn't obey the usual rules of time and space? This paradox has led some researchers to suggest that we may need entirely new types of detectors, ones that can interact with the unique, superluminal properties of tachyons. For instance, one possible detection method could involve creating a special kind of interaction that exploits the unique quantum field effects produced by tachyonic neutrinos. This could involve looking for disruptions in the quantum vacuum itself or searching for phenomena like quantum entanglement that might manifest in unusual ways due to the superluminal behavior of tachyonic particles. Yet, even with more advanced tools and detectors, one of the fundamental challenges remains: the sheer elusiveness of neutrinos, in general. They can travel through light years of lead without leaving a trace, making them notoriously difficult to observe. Tachyonic neutrinos, moving faster than light, might appear even more ephemeral, slipping through conventional detection methods. This presents a conundrum. How can we prove their existence if they defy the very methods we rely on to detect particles in the first place? This is why many physicists look to indirect evidence as the key. Rather than directly detecting tachyonic neutrinos, scientists could look for their impact on the fabric of spacetime itself. The detection of subtle distortions in spacetime, tiny ripples caused by the passage of superluminal particles, could serve as a proxy for the presence of tachions. These distortions might not be immediately observable, but if they can be measured with extreme precision, they could provide the smoking gun that confirms the existence of tachyonic neutrinos. In addition, there are theoretical models that propose that tachyonic neutrinos could interact with other exotic particles, like dark matter, in ways that would leave observable traces in large-scale cosmic structures. For example, the presence of tachyonic neutrinos could potentially affect the distribution of galaxies, the shape of galaxy clusters, or even the cosmic microwave background radiation. These signals would be incredibly faint and hard to detect, but the possibilities are exciting for physicists searching for indirect evidence of tachyons. Beyond detection, there's the question of what it means for the laws of physics if tachyonic neutrinos are real. The very existence of faster-than-light particles would call into question the foundations of causality and the nature of spacetime itself. If we accept that tachyons exist, we may have to rewrite the fundamental laws of physics. This could include revisiting well-established principles like the speed of light as a cosmic speed limit, and reconsidering the role of time in the universe. However, the idea of rewriting the laws of physics is not something that most scientists take lightly. There's a strong preference for sticking with the tried and true until new evidence makes it unavoidable to change course. After all, the framework of special relativity, which forms the backbone of our understanding of spacetime, has been incredibly successful for over a century. Yet the allure of tachyonic neutrinos is strong, especially when you consider the broader implications for the universe itself. For example, if neutrinos are tachyonic, they could provide a new mechanism for explaining the accelerating expansion of the universe. In current cosmological models, dark energy is the primary candidate for this accelerated expansion, but the exact nature of dark energy remains unknown. Tachyonic neutrinos, with their unique mass and energy characteristics, could provide an alternate explanation, or at least complement our understanding of dark energy. On the other hand, if tachyonic neutrinos are confirmed, they could open up a host of new questions about the relationship between different forces in the universe. Could they be a link between gravity and the quantum world? Could they help us understand the mysteries of dark matter or even quantum gravity? These questions are at the forefront of theoretical physics, and tachyonic neutrinos could be the key to unlocking answers. What's more, the discovery of tachyonic neutrinos could have practical applications beyond just theoretical physics. Imagine a future where the detection and manipulation of tachyonic particles becomes possible. If we could harness the superluminal properties of these particles, we might be able to develop new technologies that exploit faster-than-light communication or travel. The implications for space exploration, information transfer, and even our understanding of the fundamental nature of reality could be staggering. Yet this kind of progress will require a paradigm shift in how we approach the fundamental forces of nature. The study of tachyonic neutrinos is still in its infancy, and there's much more to learn before we can draw definitive conclusions. Still, the potential rewards of exploring this frontier are enormous, and the possibility that we could be on the verge of uncovering a new and radical chapter in the story of the universe is incredibly exciting. In many ways, tachyonic neutrinos serve as a reminder of how much we still have to learn about the universe. Despite all our technological advances and the immense progress we've made in understanding the fundamental forces, there are still mysteries lurking at the edges of our knowledge. The quest to understand tachyonic neutrinos is just one example of how science is constantly pushing the boundaries of what we know. Every new discovery raises more questions, but it also opens up new pathways for exploration, leading us deeper into the unknown. As we continue to search for answers, the story of tachyonic neutrinos serves as a powerful reminder that the universe is far more strange and mysterious than we can imagine. Whether they exist or not, they challenge our deepest assumptions about the nature of reality, inviting us to reconsider the fundamental rules that govern the cosmos. And in that pursuit, we are reminded of the true nature of scientific inquiry, to seek out the unknown, to ask questions without fear of the answers, and to explore the deepest corners of the universe, no matter how strange or paradoxical they may seem. While we don't have all the answers yet, the pursuit of tachyonic neutrinos, whether through direct detection, theoretical modeling, or indirect observation, will undoubtedly shape the future of physics. It will challenge our understanding of space, time, and the very nature of matter itself. And who knows? Maybe, just maybe, the discovery of tachyonic neutrinos will unlock a whole new chapter in the story of the universe, one that could change everything we thought we knew about reality. As we continue to delve deeper into the world of tachyonic neutrinos, we encounter a number of fascinating theoretical implications. One of the most mind-bending aspects of tachyonic neutrinos is their relationship with time. According to our current understanding of physics, particularly Einstein's theory of relativity, nothing can travel faster than the speed of light without violating the fundamental principles of causality. Causality is the cornerstone of our understanding of time and space, asserting that cause precedes effect, and that the flow of time moves in a single, unidirectional fashion. This principle has been upheld in countless experiments and observations, reinforcing our belief that time is something we cannot manipulate. But tachyonic neutrinos, if they exist, would turn this assumption on its head. If neutrinos can travel faster than light, they could, in theory, arrive before they even left, creating paradoxes where the effect precedes the cause. This opens up a realm of possibilities that challenge everything we know about how time behaves. Could it mean that the laws of causality are not as absolute as we once thought? And what does this imply for the rest of our understanding of the universe? Some scientists propose that tachyons, by their very nature, could provide a way to break free from the traditional boundaries of spacetime. If tachyons exist and can traverse the cosmos faster than light, could they also traverse time? Could they lead to the possibility of time travel, or at least open a door to alternate realities where time flows differently? The idea of time travel has long been a subject of science fiction, but the existence of tachyonic particles could offer a real, if highly theoretical, foundation for such concepts. At this stage, however, much of what we speculate about tachyonic neutrinos remains firmly within the realm of theory. While the mathematics behind their possible existence is intriguing, it's important to remember that scientific theories are only as good as the evidence that supports them. Without concrete data to back up the idea that neutrinos are faster than light particles, we're left with interesting hypotheses and the tantalizing idea that we may be on the verge of discovering something truly revolutionary. Another fascinating aspect of tachyonic neutrinos lies in their potential role in the larger structure of the universe. If these particles can move faster than light, it could mean that they are involved in processes that operate outside the normal, observable universe. Could they play a role in the formation of galaxies or the behavior of dark matter? Could they explain certain cosmological phenomena that currently elude our understanding, like the acceleration of the universe's expansion? One compelling avenue for exploration is the relationship between tachyonic neutrinos and the enigmatic substance known as dark matter. Dark matter makes up approximately 85% of the mass in the universe, yet it has remained completely invisible to traditional detection methods. It does not emit, absorb, or reflect light, making it entirely undetectable by the usual means of observation. However, we know it exists because of its gravitational effects on visible matter, such as galaxies and galaxy clusters. If tachyonic neutrinos are real, they could potentially interact with dark matter in ways we haven't yet imagined. Could tachyons be responsible for some of the phenomena we attribute to dark matter? Or perhaps they could be a crucial component of dark matter itself, explaining some of its elusive characteristics. This is where things get even more speculative. If tachyonic neutrinos are indeed part of the mysterious makeup of dark matter, we could be witnessing a fundamental shift in our understanding of the cosmos. In this scenario, tachyons might be playing a dual role, both as particles that travel faster than light and as components that help to shape the large-scale structure of the universe. They could influence the formation of stars, galaxies, and even the fabric of space-time itself. But there's another layer to this mystery. If tachyonic neutrinos can interact with dark matter in ways that we can't yet observe, what about their relationship with other fundamental forces, such as gravity? Gravity is another force that we don't yet fully understand, particularly when it comes to its relationship with quantum mechanics. Theories like quantum gravity seek to unify the gravitational force with the other three fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. But gravity, being a force that governs large-scale objects like planets and stars, behaves very differently at the quantum level. Could tachyonic neutrinos somehow bridge the gap between quantum mechanics and general relativity? Some scientists believe that particles like tachions might offer the key to unlocking this mystery. Since they would be traveling at superluminal speeds, they could provide insights into the very nature of gravity, allowing us to understand how it operates on both the quantum scale and the cosmological scale. If tachyonic neutrinos exist, they could potentially reveal new insights into the workings of space-time and the gravitational force, helping to answer some of the biggest questions in physics. Another potential avenue for exploration is the relationship between tachyonic neutrinos and the quantum field. Quantum field theory is the framework that underpins all of particle physics, describing how particles interact with fields and each other. The idea that a particle could travel faster than light introduces a whole new set of possibilities within this framework. If tachyons are real, they might not just be exotic particles. They could be manifestations of deeper quantum processes that we don't yet understand. Could they reveal hidden symmetries in nature? Could they be linked to the elusive Higgs boson, or to other particles that are yet to be discovered? The study of tachyonic neutrinos also ties into the ongoing search for a unified theory of physics, sometimes called the theory of everything. This is the idea that all of the fundamental forces and particles of the universe can be explained by a single, elegant theory. If tachyonic neutrinos exist, they might be an essential component of such a theory. Their superluminal properties could provide a missing link between quantum mechanics, general relativity, and the mysterious dark energy that drives the expansion of the universe. Tachyonic neutrinos could represent a new frontier in our quest for a unified understanding of the universe. As we continue to explore the theoretical implications of tachyonic neutrinos, it's clear that we are standing at the edge of a new era in physics. The existence of these particles would not only challenge our current understanding of the universe, but it could also open up entirely new fields of research. From the mysteries of time and causality to the elusive nature of dark matter and gravity, the discovery of tachyonic neutrinos would revolutionize nearly every aspect of our understanding of reality. But before we can make any definitive conclusions, we must continue to push the boundaries of science. The hunt for tachyonic neutrinos will require new tools, new ideas, and perhaps even a new way of thinking about the very nature of the universe. It is an exciting time for physicists and cosmologists alike, as we are on the cusp of uncovering one of the most profound secrets of the cosmos. Whether or not tachyonic neutrinos are real, their study will undoubtedly lead to new insights that could change the course of scientific discovery for generations to come. As we continue this journey into the world of tachyonic neutrinos, there are several more layers of complexity to explore. One critical area of focus is the potential impact of tachyonic neutrinos on our understanding of particle physics. Traditionally, the standard model of particle physics has served as the framework for understanding the fundamental forces and particles that make up the universe. However, the standard model is not complete. It has gaps. Most notably, it doesn't include gravity, and it doesn't fully account for dark matter or dark energy. If tachyonic neutrinos are proven to exist, they could help fill some of these gaps, offering new insights into the behavior of particles at the smallest scales. The discovery of tachyonic neutrinos could force a complete reevaluation of our understanding of quantum mechanics. Quantum theory, as we know it, describes how particles behave at incredibly small scales, such as the level of atoms and subatomic particles. This theory has been incredibly successful in explaining the behavior of the universe at this scale, yet there are still unresolved issues, especially when trying to reconcile quantum mechanics with the force of gravity. tachyonic neutrinos, with their superluminal speeds, could offer a new approach to this dilemma. They might represent a link between the quantum realm and the larger universe. Understanding how they interact with the quantum fields that permeate the universe could shed light on how particles acquire mass, how they interact with gravity, and perhaps even how we might eventually unify all the fundamental forces into a single theory. Moreover, tachyonic neutrinos might offer clues to some of the unresolved mysteries of particle physics, such as the nature of neutrino oscillations. Neutrinos are known to change between different flavors, electron, muon, and tau neutrinos, as they travel through space. This phenomenon has been observed in various experiments, and has led to the discovery that neutrinos have mass, which was once thought impossible. Could tachyonic neutrinos, with their faster-than-light properties, somehow be linked to this unusual behavior? Could their superluminal speeds influence the oscillations of neutrinos in ways we haven't yet considered? Furthermore, the exploration of tachyonic neutrinos could also extend into the realm of quantum field theory and the study of vacuum states. In quantum field theory, the vacuum is not empty but rather a seething, dynamic environment filled with virtual particles constantly popping in and out of existence. Could tachyonic neutrinos interact with this vacuum in unique ways, revealing previously unknown properties of the quantum field? Could their superluminal speeds allow them to bypass certain quantum constraints, potentially opening up new avenues for understanding how the universe behaves at the most fundamental level? In addition, tachyonic neutrinos may hold the key to understanding some of the most puzzling phenomena in cosmology. For instance, the cosmic microwave background (CMB) radiation, thought to be the afterglow of the Big Bang, provides a snapshot of the universe when it was just 380,000 years old. The CMB contains subtle imprints of the universe's early structure, but its exact nature is still a subject of much debate. If tachyonic neutrinos are part of the cosmic fabric, they could have played a role in shaping the early universe in ways that we don't yet fully comprehend. Their interactions could have left traces in the CMB that we have yet to detect. This would open up exciting possibilities for further study, as the discovery of such imprints could give us a deeper understanding of the universe's birth and its evolution. Even more intriguingly, tachyonic neutrinos might provide insight into some of the most elusive aspects of the universe itself, such as the nature of dark energy. Dark energy is the mysterious force that is driving the accelerated expansion of the universe, yet we have little idea of what it actually is. Some theories suggest that dark energy could be related to a cosmological constant that fills all of space, while others propose that it arises from the properties of certain types of fields or particles. Could tachyonic neutrinos be tied to dark energy? Since these particles would travel faster than light, it's possible that they could interact with the fabric of spacetime in a way that influences the expansion of the universe. If tachyonic neutrinos can affect spacetime itself, they might play a role in the mysterious force that causes galaxies to move away from each other at ever-increasing speeds. There are also fascinating questions about the potential uses and implications of tachyonic neutrinos in future technologies. If we can prove the existence of these particles and develop a method of detecting them, it could open up entirely new avenues for practical applications. Could tachyonic neutrinos be harnessed in ways similar to how we currently use light and electromagnetic waves? Could they form the basis for a new kind of communication or transportation that exploits their superluminal speeds? The idea of using tachyonic neutrinos for faster-than-light communication is particularly intriguing. If we could find a way to manipulate and control these particles, it might be possible to send information across vast distances in a fraction of the time it would take using current technology. This would have profound implications for everything from space exploration to global communication. However, before we get ahead of ourselves, it's important to note that the practical use of tachyonic neutrinos, if they exist, remains highly speculative. We are still a long way from understanding these particles well enough to use them in any practical capacity. Much more research is needed to verify their existence, understand their properties, and figure out how we might interact with them in a controlled way. Nevertheless, the very idea that such particles could exist and that they might one day be harnessed for technological applications is a tantalizing prospect. As with any groundbreaking scientific theory, the potential discovery of tachyonic neutrinos also raises a host of philosophical and ethical questions. If these particles exist and have the ability to travel faster than light, what does this mean for our understanding of reality itself? Does it suggest that our universe is far more complex and mysterious than we ever imagined? And if we are able to manipulate such particles, what responsibilities will we have in doing so? Could the use of tachyonic neutrinos have unintended consequences on the fabric of space-time, or the fundamental laws of physics? Could we be opening a Pandora's box, exposing ourselves to dangers we cannot yet comprehend? These questions highlight the complexity of our quest to understand the universe. As we probe deeper into the nature of reality, we are constantly confronted with new mysteries and new challenges. The discovery of tachyonic neutrinos, if it ever happens, will be one of the most profound breakthroughs in the history of science. It could reshape everything we know about the universe, from the smallest particles to the largest structures, and it could open up entire new fields of study. The implications of such a discovery are so vast that it's difficult to fully comprehend their scope. But one thing is certain, the journey to uncover the truth about tachyonic neutrinos is only just beginning, and it will undoubtedly take us to places we never thought possible. The theory of tachyonic neutrinos represents one of the most exciting and challenging frontiers in modern physics. While we are still far from proving their existence, the theoretical implications of these particles are profound. From challenging our understanding of time and causality to potentially unlocking the secrets of dark matter and dark energy, tachyonic neutrinos could revolutionize our understanding of the universe. As we continue to explore this fascinating topic, we are bound to uncover new insights that will push the boundaries of science and perhaps even lead to breakthroughs that change the course of human history. Whether or not tachyonic neutrinos turn out to be real, their study is sure to inspire new theories, new technologies, and new ways of thinking about the cosmos. The search for these elusive particles is far from over, and the journey has only just begun. Continuing on the exciting possibilities that tachyonic neutrinos bring, we need to dive deeper into the practical challenges scientists face as they try to understand these particles. Despite the theoretical fascination with tachyonic neutrinos, there are considerable hurdles standing in the way of their confirmation and study. The most significant of these challenges is the fundamental nature of neutrinos themselves. Neutrinos are notoriously difficult to detect. Unlike other particles that interact more easily with matter, neutrinos rarely interact with anything. This is why they've earned the nickname ghost particles. Their interaction with other particles is so minimal that they can travel through entire planets without being affected. This makes their detection incredibly difficult, even in the best particle accelerators or detectors designed to catch elusive particles. The neutrinos that we do detect are typically those produced in massive quantities, such as in the Sun or from nuclear reactions on Earth. Detecting individual tachyonic neutrinos, if they exist, would require completely new techniques, technology, and a level of precision that has yet to be achieved. The detection challenge is compounded by the fact that tachyonic neutrinos, by their very nature, would travel faster than light. Current detection systems are built with the assumption that neutrinos move at sublight speeds. The sensors, designed to detect interactions as neutrinos pass through various detectors, might not be capable of recognizing these faster-than-light particles in real time. Their superluminal speed could lead to phenomena that are beyond our current scientific understanding. For instance, it's unclear what would happen if a tachyonic neutrino interacted with a detector designed for slower particles. Would it even register in the traditional sense? Or would the interaction be so different from what we expect that it might go unnoticed or misinterpreted? This brings us to the crucial issue of theory versus reality. Theoretical models have predicted that tachyonic neutrinos could exist, but those models are still far from complete. They make bold predictions about how these particles might behave under certain conditions, but the actual conditions needed for their creation, detection, and study are not fully understood. Much like the discovery of the Higgs boson or gravitational waves, confirming the existence of tachyonic neutrinos would require breakthroughs in both theoretical physics and experimental technology. It's possible that our current understanding of particle detectors is simply too limited to detect these particles, and that new, more advanced detectors will be needed to make the breakthrough. Tachyonic neutrinos also challenge our understanding of space and time itself. One of the primary reasons why faster-than-light particles are so controversial is that they break fundamental principles of relativity. According to Einstein's theory of special relativity, nothing can travel faster than the speed of light in a vacuum. The very concept of superluminal particles like tachyons contradicts this principle. If tachyonic neutrinos exist and travel faster than light, it could mean that our understanding of the laws governing spacetime needs to be revised. Some theorists even suggest that tachyonic neutrinos could be a gateway to understanding how the universe might work in ways that defy current models. For example, the nature of causality itself could be thrown into question. In the realm of relativity, events that occur in the universe have a specific order. One event causes another, and this causal chain maintains the consistency of time. Superluminal particles could potentially violate this chain, leading to paradoxes. If a particle can travel faster than light, it might be able to arrive before it even departs, creating situations where cause and effect become blurred. The discovery of tachyonic neutrinos would force scientists to reconsider how causality works, and possibly lead to a redefinition of time itself. Another theoretical idea is that tachyonic neutrinos could be related to the structure of spacetime at the quantum level. In the quest for a unified theory that combines quantum mechanics and general relativity, tachyons could play a critical role. The theory of quantum gravity, which seeks to describe the gravitational force within the framework of quantum mechanics, might find new insights if tachyonic neutrinos are discovered. These particles could serve as a kind of bridge between the two realms, quantum mechanics on the small scale and general relativity on the large scale. Their behavior might reveal how gravity operates at the quantum level, a question that has long puzzled scientists. To understand how tachyonic neutrinos might work within this framework, we must first explore some of the concepts in quantum field theory, QFT. QFT suggests that all particles are excitations in their respective fields, and these fields permeate all of space. The fields governing neutrinos are part of the standard model of particle physics. If tachyonic neutrinos exist, they would likely be excitations of a different kind of field, one that could interact with other fields in ways we don't fully understand yet. This would be revolutionary in terms of how we think about particles, fields, and spacetime itself. A new type of field could potentially interact with the vacuum, altering the way energy and mass behave in the universe. Interestingly, there is also the possibility that tachyonic neutrinos might be connected to the multiverse theory. This theory suggests that our universe is just one of many in a vast, possibly infinite, multiverse. In this context, tachyonic neutrinos might serve as a kind of link between these different universes. Their superluminal speed could allow them to travel across different regions of spacetime that are not connected in the conventional sense. Perhaps tachyonic neutrinos could help scientists explore the fabric of the multiverse, offering a glimpse into other realities that are beyond our observational capabilities. Some scientists have even proposed that tachyonic neutrinos could help us understand the origins of the universe itself. If they are indeed capable of existing at superluminal speeds, these particles could potentially offer clues about the early moments of the Big Bang. During that time, the universe was in an extremely hot, dense state, with energy and matter behaving in ways that are difficult for us to comprehend. It's possible that tachyonic neutrinos played a role in shaping the early universe, and their study could help us unlock the secrets of the Big Bang and the very first moments of creation. This brings us to the speculative aspect of tachyonic neutrinos. While the theoretical models are compelling, there's still much we don't know about how these particles might fit into the larger cosmic puzzle. As with any radical new idea, the evidence for their existence is currently theoretical. However, the pursuit of this knowledge pushes the boundaries of our scientific understanding. Whether or not tachyonic neutrinos turn out to be real, the search for them will likely lead to new discoveries about the nature of reality itself. Ultimately, the exploration of tachyonic neutrinos is a journey into the unknown. It's an inquiry that could redefine our understanding of physics, cosmology, and the very structure of the universe. The quest to detect and understand these particles is part of a larger endeavor to explore the deepest mysteries of the cosmos. Questions about time, space, matter, and energy that have baffled humanity for centuries. Whether or not tachyonic neutrinos exist, the pursuit of knowledge continues to fuel our curiosity and drive our quest to uncover the secrets of the universe. As we continue to explore the fascinating world of tachyonic neutrinos, we must consider their potential impact on future scientific developments. If these particles were to be confirmed and studied, they could drastically alter the way we approach both theoretical and experimental physics. For example, their existence could push us to reevaluate some of the most fundamental aspects of our physical theories. One of the most immediate areas of impact would likely be in the study of particle physics. The discovery of tachyonic neutrinos could lead to the development of entirely new theoretical models. Much of our current understanding of particle physics is based on the Standard Model, which has been incredibly successful in describing a wide range of particle interactions. However, the Standard Model is not complete. It doesn't include gravity, nor does it explain certain phenomena, like dark matter and dark energy. Tachyonic neutrinos could potentially be the key to bridging the gaps in our understanding. They could open the door to new theoretical frameworks that include gravity and other unexplained cosmic phenomena. Such breakthroughs could have profound implications for fields beyond just theoretical physics. For example, advancements in particle physics could lead to new technologies in energy production and materials science. The techniques developed to study and understand tachyonic neutrinos could have applications that extend far beyond the lab. In fact, throughout history, many of the most significant technological advances have been born from the exploration of abstract scientific theories. From the invention of lasers, which were originally theoretical constructs in quantum mechanics, to the development of computer technology, which arose from the study of subatomic particles, the pursuit of seemingly esoteric knowledge has frequently led to breakthroughs that impact our everyday lives. Of course, any practical application of tachyonic neutrinos would require enormous advances in technology. As mentioned earlier, the challenge of detecting neutrinos, and even more so tachyonic neutrinos, is not trivial. The sensors and equipment we currently use to detect neutrinos are far from capable of measuring particles moving faster than light. We would need to develop entirely new detection technologies that can capture these superluminal particles. This would likely involve both theoretical and technological innovations, drawing from fields like quantum mechanics, general relativity, and materials science. Moreover, the detection of tachyonic neutrinos might provide a new way of probing the fabric of spacetime itself. Since these particles are theoretically faster than light, they could provide insights into the fundamental structure of the universe, potentially revealing properties of space and time that we have yet to understand. For example, we could learn more about the nature of spacetime at extremely high energies or the behavior of quantum fields in the presence of extreme gravitational forces. The implications of these discoveries could revolutionize our understanding of everything from black holes to the Big Bang. Furthermore, the existence of tachyonic neutrinos could impact our understanding of the universe's largest and most mysterious phenomena, such as dark matter and dark energy. These two entities make up the majority of the mass and energy in the universe, yet we still don't fully understand what they are or how they behave. Tachyonic neutrinos, with their unique properties, could offer clues about the nature of dark matter and dark energy, or even provide a new way of detecting and studying these elusive phenomena. Some theorists have suggested that tachyonic neutrinos might interact with dark matter in ways that could reveal more about this mysterious substance. If tachyonic neutrinos do exist, they might provide the key to unraveling the mystery of dark matter and dark energy, two of the biggest puzzles in modern cosmology. Another area of interest is the potential relationship between tachyonic neutrinos and quantum mechanics. As previously mentioned, tachyons and neutrinos defy the traditional understanding of relativity, which states that no particle can travel faster than light. If tachyonic neutrinos exist, they could offer a unique opportunity to study the intersection of quantum mechanics and relativity, two theories that have thus far been unable to be unified into a single framework. The study of tachyonic neutrinos could shed light on this elusive goal, potentially leading to a breakthrough in our understanding of the quantum nature of spacetime. This could, in turn, inform the development of a theory of quantum gravity, which aims to describe the force of gravity at the quantum level. Theoretical physicists have long sought a unified theory that combines quantum mechanics, which governs the behavior of particles at the smallest scales, and general relativity, which describes gravity and the behavior of large objects like stars and galaxies. These two pillars of modern physics are fundamentally incompatible in their current forms, and many believe that the discovery of tachyonic neutrinos could be the key to reconciling them. If tachyonic neutrinos do indeed travel faster than light, their properties could reveal new insights into the structure of spacetime, potentially providing the missing link between quantum mechanics and general relativity. However, the road to such a discovery would not be easy. It would require not only advances in theoretical physics but also revolutionary new experimental techniques. Detecting tachyonic neutrinos would require a completely different approach to particle detection, one that can capture the unique properties of these superluminal particles. As mentioned earlier, current detectors are designed to detect slower-moving particles, and they may not be equipped to measure the faster-than-light speeds of tachyonic neutrinos. A major challenge would be to design a detector that can capture these particles without being thrown off by their superluminal speed. This could involve developing new types of sensors that can measure time and space in ways that are beyond our current capabilities. To accomplish this, scientists would likely need to explore a range of different technologies. One possible avenue could be the development of new particle accelerators that can generate and detect tachyonic neutrinos. These accelerators would need to operate at energies far beyond anything currently achievable, possibly requiring the construction of larger and more powerful machines. In addition, new materials and detection methods would need to be developed to ensure that these particles could be accurately measured. This would be a monumental task, requiring collaboration across multiple fields of physics, engineering, and technology. Another possibility is the use of advanced computational techniques to simulate the behavior of tachyonic neutrinos. While simulations can never fully replace direct observation, they can provide valuable insights into how these particles might behave and interact with other particles and fields. By modeling the behavior of tachyonic neutrinos in a controlled, simulated environment, scientists might be able to develop new theories and predictions that can then be tested through experiments. This approach could help to narrow down the possibilities and guide the search for real-world evidence of tachyonic neutrinos. In the long run, the discovery of tachyonic neutrinos could lead to entirely new branches of physics and technology. As with any major scientific breakthrough, the implications of such a discovery would be far-reaching and could extend to a wide range of fields. It might lead to new technologies for space exploration, as scientists could gain a deeper understanding of how particles interact with the fabric of spacetime. It could also lead to advancements in energy production and storage, as new insights into the behavior of particles might unlock more efficient ways of generating and harnessing energy. The theory of tachyonic neutrinos is one of the most exciting and mysterious areas of modern physics. While their existence remains speculative, the potential implications of their discovery are vast. From altering our understanding of space and time to providing new insights into the nature of dark matter and dark energy, tachyonic neutrinos could revolutionize our understanding of the universe. The pursuit of these particles could lead to groundbreaking advancements in both theory and technology, and might ultimately help us answer some of the deepest questions in science. As our tools and techniques for studying the cosmos continue to evolve, the search for tachyonic neutrinos may one day provide the key to unlocking the next great chapter in the story of the universe. As we continue to contemplate the profound impact that tachyonic neutrinos could have on our understanding of the universe, we must consider their potential role in shaping the future of cosmology. Their discovery could influence not only our comprehension of fundamental physics, but also our approach to studying the very fabric of the cosmos. The implications of tachyonic neutrinos extend beyond theoretical and experimental physics, reaching into areas that we haven't yet begun to fully explore. One possible area where tachyonic neutrinos could make a significant contribution is in our understanding of the early universe. The study of neutrinos has already provided insights into the formation of the universe, particularly in the moments following the Big Bang. By observing the cosmic microwave background radiation, scientists have gathered evidence of the processes that took place during the early stages of the universe. However, these observations are limited by the physics we currently understand. Tachyonic neutrinos could potentially offer a new way of probing the early universe. If they exist, they could have interacted with other particles in ways that would leave an imprint on the cosmos, much like the way the cosmic microwave background radiation reflects the state of the universe shortly after the Big Bang. By studying the behavior of tachyonic neutrinos, scientists could gain new insights into the dynamics of the early universe, possibly even identifying new phases of matter or exotic interactions that occurred during this critical period. This could provide a more complete picture of how the universe evolved from its first moments to its present state. Moreover, the existence of tachyonic neutrinos could challenge our current understanding of the Big Bang itself. Traditional models of cosmology suggest that the universe began with a singularity, an infinitely small point where all matter and energy were concentrated. From this point, the universe began to expand, eventually cooling and evolving into the universe we observe today. However, the introduction of superluminal particles like tachyonic neutrinos could suggest an alternative view of the Big Bang, where the expansion of the universe may have involved faster-than-light particles and interactions that we have yet to account for. This could lead to new models of cosmic inflation, the rapid expansion of the universe in the moments following the Big Bang, and provide a more complete picture of the forces that shape the universe. Tachyonic neutrinos could also play a pivotal role in our search for a theory of everything. For decades, physicists have sought to reconcile the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single, unified framework. This is the ultimate goal of string theory and other advanced theoretical models, which aim to describe all of the interactions in the universe through a single, elegant equation. The discovery of tachyonic neutrinos could provide the missing piece of this puzzle. By studying the interactions between tachyonic neutrinos and other particles, scientists might gain a deeper understanding of the connections between the fundamental forces. This could lead to the development of a unified theory of everything, one that could explain all physical phenomena in a single framework. In addition, tachyonic neutrinos could have important implications for the study of quantum mechanics. The realm of quantum mechanics is governed by the strange and counterintuitive behaviors of subatomic particles. Phenomena such as wave-particle duality and quantum entanglement have led scientists to rethink the very nature of reality itself. Tachyonic neutrinos, with their ability to exceed the speed of light, would introduce even more bizarre elements to this already perplexing field. Their discovery could push us to reconsider the fundamental principles of quantum mechanics and the limits of quantum theory. It might prompt scientists to explore new theories of quantum gravity, which aim to merge the principles of quantum mechanics with the theory of general relativity. Such a development could lead to groundbreaking advances in our understanding of the quantum world and the nature of spacetime. Another fascinating aspect of tachyonic neutrinos is the potential they hold for space exploration. As we push the boundaries of space travel, we are constantly seeking new methods to accelerate spacecraft to unprecedented speeds. Currently, our best propulsion systems are limited by the constraints of Newtonian physics and relativistic speeds. The discovery of tachyonic neutrinos could revolutionize the way we think about space travel, offering new possibilities for faster-than-light travel and communication. If tachyonic neutrinos can travel faster than light, it's possible that we could harness this phenomenon to propel spacecraft across vast distances in space, potentially opening the door to interstellar travel. One of the most intriguing possibilities is the idea that tachyonic neutrinos could offer a method for faster-than-light communication. If we can detect and manipulate these superluminal particles, it might be possible to send signals across the cosmos at speeds that far exceed the speed of light. This could revolutionize our ability to communicate with distant spacecraft or colonies, making interstellar communication a reality. It could also lead to advancements in quantum communication, a field that already promises to reshape our approach to secure data transmission. By exploiting the properties of tachyonic neutrinos, we might be able to create a new form of communication that is both faster and more secure than anything we currently have. As we delve deeper into the implications of tachyonic neutrinos, we must also consider their potential impact on other fields of science and technology. The discovery of these particles could lead to advancements in everything from quantum computing to energy production. For instance, understanding how tachyonic neutrinos interact with other particles could inspire new types of energy sources or power generation methods. The study of these particles might also lead to breakthroughs in materials science, particularly in the development of new materials that can withstand extreme conditions or exhibit previously unknown properties. On a broader scale, the discovery of tachyonic neutrinos could change the way we think about the universe itself. These particles could provide evidence that the universe operates in ways we cannot yet fully comprehend, offering a glimpse into the hidden dimensions and forces that govern reality. This could lead to a paradigm shift in our understanding of the cosmos, where space, time, and matter behave in ways that challenge everything we thought we knew. The discovery of tachyonic neutrinos could inspire a new era of exploration, where the boundaries of science are pushed beyond their current limits, and the unknown is embraced as the next frontier. Despite the promising potential of tachyonic neutrinos, it's important to remember that we are still far from understanding whether these particles truly exist. Theoretical models and experiments have yet to provide conclusive evidence for their existence, and the detection of faster-than-light particles presents a formidable challenge. For now, tachyonic neutrinos remain a speculative concept, one that exists in the realm of theoretical physics rather than established fact. However, the very fact that we are exploring the possibility of such particles highlights the relentless curiosity and ingenuity that drives scientific discovery. If tachyonic neutrinos are eventually confirmed, they could mark one of the most significant breakthroughs in the history of science. They could alter our understanding of the universe in ways that we can scarcely imagine, pushing the boundaries of knowledge and inspiring new generations of scientists and explorers. As we continue to investigate the mysteries of the universe, the search for tachyonic neutrinos will remain one of the most intriguing and exciting quests in modern physics. The discovery of tachyonic neutrinos may not only deepen our understanding of the cosmos, but also open up new avenues for technological innovation and exploration. The journey to uncover the truth about these elusive particles is only just beginning, and as our tools and knowledge evolve, so too will our ability to answer the questions that have long perplexed us. Whether they exist or not, the pursuit of tachyonic neutrinos represents the very essence of scientific progress, an unyielding quest to explore the unknown and expand the boundaries of human understanding. As we continue to explore the potential of tachyonic neutrinos, it's essential to understand the broader context in which this search is unfolding. In the landscape of modern physics, where the pursuit of understanding the very nature of reality is unceasing, tachyonic neutrinos fit into an ongoing effort to reconcile seemingly incompatible theories. They challenge the foundations of both quantum mechanics and relativity, two pillars of modern physics that have stood the test of time but have yet to be fully unified. One of the most significant hurdles in modern physics is the clash between general relativity, which governs the behavior of large-scale objects like planets, stars, and galaxies, and quantum mechanics, which describes the behavior of the smallest particles. These two frameworks are incredibly successful in their respective domains but do not fit together seamlessly. General relativity operates within the framework of spacetime and gravity, while quantum mechanics relies on the probabilistic nature of subatomic particles. Tachyonic neutrinos, as hypothetical superluminal particles, could provide clues to how these two frameworks might be reconciled. In particular, their behavior might suggest a new way to integrate the quantum field theory of particles with the geometric description of spacetime provided by general relativity. If tachyonic neutrinos exist and behave as predicted by certain theoretical models, it might offer a glimpse into a quantum theory of gravity, a theory that has eluded scientists for decades. Such a breakthrough would be one of the most profound in the history of physics, offering not only a better understanding of neutrinos but also a new way of viewing the universe itself. Tachyonic neutrinos could also play a crucial role in testing the limits of the standard model of particle physics, which has been the foundation of our understanding of fundamental particles for over 50 years. The Standard Model has successfully explained the behavior of all known particles and their interactions, except for gravity. However, it does leave some unanswered questions, such as the nature of dark matter and dark energy, the origins of mass, and the mysteries surrounding neutrinos themselves. The existence of tachyonic neutrinos would require an extension or modification of the Standard Model, and this could lead to a more comprehensive theory that accounts for all forces, including gravity. One interesting possibility is that the behavior of tachyonic neutrinos could shed light on the nature of dark matter and dark energy, two of the most profound mysteries in modern astrophysics. Dark matter, which accounts for roughly 27% of the universe's mass, and dark energy, which makes up about 68% of the universe, are both invisible and detectable only through their gravitational effects. Understanding their nature is one of the key goals of modern cosmology, and tachyonic neutrinos could provide a clue to their origin or composition. If tachyonic neutrinos exist, they might interact with dark matter or dark energy in ways that we cannot currently detect. For example, these particles could be part of a larger family of exotic particles that make up dark matter. Alternatively, they might play a role in the expansion of the universe, contributing to the acceleration observed in the cosmic expansion due to dark energy. Understanding how tachyonic neutrinos interact with these mysterious substances could provide the breakthrough needed to unlock the secrets of dark matter and dark energy. The search for tachyonic neutrinos could also have profound implications for our understanding of particle physics beyond the Standard Model. As scientists continue to explore the subatomic world, they are looking for ways to extend the Standard Model into a more comprehensive theory. One of the most promising avenues for this is the theory of supersymmetry, which proposes that each known particle has a corresponding superpartner particle. Tachyonic neutrinos, if they exist, could fit into this framework, potentially revealing new symmetries in the fundamental forces of nature. Supersymmetry is a theory that aims to solve several problems in particle physics, such as the hierarchy problem, why the weak force is much weaker than gravity, and the nature of dark matter. If tachyonic neutrinos are discovered, they could be the missing link that connects the Standard Model to supersymmetry, opening up new avenues for research into particle physics and cosmology. This could lead to a deeper understanding of the fundamental forces and particles that make up the universe, and provide a foundation for a new era of scientific exploration. Beyond particle physics, the discovery of tachyonic neutrinos could also have implications for technology. As we learn more about these elusive particles, we might discover new ways to manipulate them or harness their unique properties. For example, the ability to detect or even generate tachyonic neutrinos could lead to new advances in communication, computation, and energy generation. The speed at which these particles travel could make them useful in developing faster and more efficient communication systems, potentially revolutionizing data transmission in ways we can't yet fully envision. Tachyonic neutrinos could also provide a new way to probe the most extreme environments in the universe, such as the interiors of black holes or the early moments of the Big Bang. These environments are currently inaccessible to direct observation, but the unique properties of tachyonic neutrinos might allow us to gather information about them indirectly. For instance, if tachyonic neutrinos could pass through regions of space that other particles cannot, they could offer a way to study the conditions inside black holes or the aftermath of cosmic events like supernovae. As with any groundbreaking discovery, the potential of tachyonic neutrinos is accompanied by challenges. One of the major obstacles is the difficulty in detecting them. Since these particles are hypothesized to travel faster than light, they would likely interact very weakly with other matter. This means that, even if tachyonic neutrinos exist, they would be incredibly difficult to detect with current technology. New detectors and more sophisticated experiments would be necessary to confirm their existence and study their properties in detail. However, the reward for such efforts could be immense, as the discovery of these particles could lead to a deeper understanding of the universe and potentially unlock new technologies that we can only imagine. Additionally, the search for tachyonic neutrinos raises important questions about the nature of time and causality. The idea that particles could travel faster than light challenges our traditional understanding of cause and effect. In relativity, the speed of light is considered the ultimate limit, beyond which events cannot influence one another in a cause and effect relationship. If tachyonic neutrinos are real, they could force us to reevaluate our understanding of causality and time itself, leading to profound philosophical and scientific implications. As the search for tachyonic neutrinos continues, the very fact that such particles are being considered opens up new ways of thinking about the universe. Whether or not these particles exist, the quest to understand them pushes the boundaries of science, prompting new theories, experiments, and insights into the nature of reality. It is this kind of curiosity-driven research that has led to some of the most transformative discoveries in history, from the discovery of the electron to the understanding of quantum mechanics and the structure of the atom. The pursuit of tachyonic neutrinos represents a continuation of this tradition, where the unknown beckons us to explore it and expand our understanding of the universe. Whether we ultimately find tachyonic neutrinos or not, their search represents the forefront of modern physics, an exciting exploration into the depths of space, time, and the very fabric of reality itself. The pursuit of knowledge, in this case, is just as important as the discovery itself. Through this journey, we are not just searching for new particles, but for a deeper understanding of the cosmos and our place within it. As we continue our exploration into the realms of tachyonic neutrinos, it's important to consider the broader implications that their discovery or non-discovery might have on scientific theory and technological progress. Imagine, for a moment, the impact of a fundamental particle that could travel faster than light. The very nature of the laws of physics could be challenged, and new paradigms might emerge. In the same way that the discovery of the electron in the late 19th century revolutionized our understanding of the atom and led to the development of quantum mechanics, the discovery of tachyonic neutrinos could catalyze an era of scientific breakthroughs. It could signal a new phase in the search for a unified theory of everything, a theory that could eventually explain the workings of the entire universe from the smallest subatomic particles to the vast cosmic structures. One of the most fascinating aspects of tachyonic neutrinos is their potential role in the quest for a unified theory of physics, often referred to as a theory of everything, TOE. This is a theory that aims to integrate all the fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single, cohesive framework. For centuries, physicists have been trying to unite these forces, but so far, no theory has been able to reconcile quantum mechanics with general relativity, the theory that describes gravity on a large scale. While quantum mechanics explains the behavior of subatomic particles, it fails to account for the force of gravity, which is described by general relativity. In contrast, general relativity works perfectly for large-scale structures like planets, stars, and galaxies but does not provide insights into the quantum realm. Tachyonic neutrinos could serve as a bridge between these two domains. The fact that they are predicted to move faster than light suggests that they might be subject to different laws of physics than those that govern ordinary particles. If we could study them in detail, it might provide us with crucial insights into how to reconcile these two theories. Perhaps, as some theorists speculate, the existence of tachyonic neutrinos could point the way toward a new, unified theory that encompasses both quantum mechanics and general relativity. Another key aspect of tachyonic neutrinos is their potential role in our understanding of the early universe. The study of neutrinos has already been instrumental in piecing together the events of the Big Bang and the formation of the universe. For example, the detection of cosmic neutrinos, those that were produced in the early moments of the universe's existence, has given us valuable information about the conditions that prevailed shortly after the Big Bang. These neutrinos, however, are ordinary neutrinos, not tachyonic ones. If tachyonic neutrinos exist, they could have been produced in even larger quantities in the earliest moments of the universe, potentially leaving a signature that could be detectable today. The study of tachyonic neutrinos might also give us clues about the mysterious force known as dark energy, which is responsible for the accelerated expansion of the universe. Dark energy makes up about 68% of the total energy in the universe, but its nature remains one of the most profound mysteries in science. Tachyonic neutrinos, if they exist, could potentially interact with dark energy in ways that we are only beginning to understand. Perhaps they could provide a direct link between the behavior of these particles and the phenomena of cosmic expansion. If tachyonic neutrinos could be shown to interact with dark energy in a significant way, it might lead to a deeper understanding of the forces driving the expansion of the universe. As we push further into the unknown, we must also confront the challenges that come with investigating tachyonic neutrinos. One of the primary difficulties in detecting these elusive particles is their incredibly weak interaction with matter. Neutrinos, in general, are notoriously difficult to detect because they rarely interact with other particles. Ordinary neutrinos are produced in vast quantities by the Sun, nuclear reactors, and cosmic events like supernovae, yet they pass through the Earth as if it weren't even there, rarely interacting with the atoms in our planet. The difficulty of detecting these particles means that even if tachyonic neutrinos exist, they would be incredibly difficult to observe with current technology. To overcome this challenge, scientists would need to develop new techniques and technologies capable of detecting particles that are predicted to travel faster than light. This might involve building more sensitive detectors capable of picking up the faintest signals from these particles. It might also require innovative new methods of observing the interactions of tachyonic neutrinos with other particles, such as through their effects on the cosmic microwave background radiation, or their influence on the large-scale structure of the universe. In addition to the technological challenges, the very concept of faster-than-light particles raises fundamental questions about the nature of space and time. According to Einstein's theory of relativity, nothing can travel faster than the speed of light because this would violate causality, the principle that causes must precede effects. If tachyonic neutrinos exist and move faster than light, it could lead to paradoxes where events seem to happen before their causes. This is an area of intense debate within the scientific community, as it challenges our most basic understanding of how the universe works. Despite these challenges, the potential rewards of discovering tachyonic neutrinos are immense. If these particles exist, they could open up entirely new fields of research, from particle physics to cosmology to quantum mechanics. They could provide answers to some of the most profound questions in science, such as the nature of dark matter and dark energy, the fate of the universe, and the ultimate fate of the fundamental forces of nature. In this way, the search for tachyonic neutrinos represents not just a quest to understand a specific type of particle but a broader journey toward uncovering the deepest truths of the universe. Moreover, the discovery of tachyonic neutrinos could also have profound implications for technology and our everyday lives. As we learn more about these particles, we might uncover new ways to manipulate them or harness their unique properties. For example, their superluminal speed could be used to create faster communication networks, potentially revolutionizing the way information is transmitted across the world. Similarly, the study of tachyonic neutrinos could lead to new methods of energy generation, or even entirely new forms of technology that we can't yet fully imagine. The potential applications of tachyonic neutrinos are vast and varied, and we are only beginning to scratch the surface of what they could mean for science and technology. If we are able to detect these particles and study their properties, we could be on the verge of a new era of scientific discovery, one that could reshape our understanding of the universe and our place within it. Tachyonic neutrinos are not just hypothetical particles, they represent a frontier in the ongoing quest for knowledge. Their discovery, or even their theoretical understanding, could lead to groundbreaking advances in multiple areas of science, from particle physics to cosmology to technology. Whether or not they exist, the search for tachyonic neutrinos challenges our understanding of the universe and pushes the boundaries of what we know about the fundamental forces of nature. In the end, it is the pursuit of these unknowns, these mysteries of the universe, that drives scientific progress and inspires new generations of thinkers and explorers. The study of tachyonic neutrinos is just one piece of the puzzle, but it is a piece that could ultimately unlock new realms of understanding. It serves as a reminder that, in science, there are always new frontiers to explore, and the most profound discoveries often come from the most unexpected places. As we continue to push the boundaries of knowledge, the universe, both in its vastness and its smallest details, remains a source of infinite wonder and endless possibility. As we continue to delve deeper into the world of tachyonic neutrinos, it becomes evident that their possible existence carries profound implications not only for the future of fundamental physics, but also for the way we perceive the very fabric of reality itself. If tachyonic neutrinos do exist, they would challenge some of the most well-established principles of modern physics, particularly our understanding of space, time, and causality. To appreciate the significance of tachyonic neutrinos fully, we must first explore the fundamental principles of relativity, which would be directly challenged by their existence. Einstein's theory of relativity has been a cornerstone of modern physics since the early 20th century. The special theory of relativity posits that nothing can travel faster than the speed of light, a principle that has been confirmed by numerous experiments and observations. According to this theory, if a particle were to exceed the speed of light, it would violate causality, the principle that events occur in a specific order, with causes preceding effects. Tachyonic neutrinos, by definition, would be particles that exceed the speed of light. If they exist, they could potentially undermine the core tenets of relativity. For instance, imagine a situation in which a tachyonic neutrino travels from point A to point B faster than light. In this scenario, the particle might reach point B before it even leaves point A, creating a paradox where the effect precedes the cause. This type of situation would raise fundamental questions about the very nature of time and causality. Could the concept of time itself need to be redefined to account for particles that break the light-speed barrier? This dilemma is not just theoretical. The very existence of tachyonic neutrinos could force physicists to rethink how we understand time travel and the nature of events in the universe. If particles can travel faster than light, what implications would this have for our understanding of time? Could tachyonic neutrinos lead us to an entirely new theory of time, one that allows for phenomena previously thought to be impossible, such as backward time travel, or even the manipulation of time itself? Interestingly, some theories in theoretical physics have already explored the idea of faster-than-light particles and their potential implications. One such concept is the idea of closed time-like curves, which are loops in spacetime that could, in theory, allow for time travel. While closed time-like curves are purely theoretical at this stage, the discovery of tachyonic neutrinos could provide an experimental basis for these ideas, allowing scientists to test the limits of our understanding of time and space. Furthermore, the existence of tachyonic neutrinos could provide new insights into the nature of space itself. According to some theories, the fabric of spacetime is not a static, unchanging backdrop but is instead dynamic and malleable. If tachyonic neutrinos exist, they might interact with spacetime in ways that we cannot yet fully comprehend. For example, their superluminal speed might suggest that they could warp spacetime in unusual ways, potentially offering clues about the nature of gravity and the overall structure of the universe. This line of inquiry is particularly intriguing in the context of string theory, which is one of the leading candidates for a theory of everything. String theory posits that the fundamental particles we observe in nature are not point-like objects, but rather tiny vibrating strings. These strings could, in theory, interact with one another in ways that we are only beginning to understand. The potential interaction between tachyonic neutrinos and the strings in string theory could provide new insights into the quantum nature of spacetime and the behavior of forces at the smallest scales. One of the key challenges in studying tachyonic neutrinos is their extremely weak interaction with matter. Neutrinos, in general, are known for their elusive nature. They interact only via the weak nuclear force, which is much weaker than the electromagnetic force, and they can pass through vast amounts of matter without being detected. This makes it incredibly difficult to observe neutrinos in the first place, let alone tachyonic neutrinos, which are predicted to have even more exotic properties. To detect tachyonic neutrinos, scientists would likely need to develop entirely new experimental techniques, ones that can capture the subtle effects of these superluminal particles. For example, researchers could use advanced detectors that are sensitive to the rare interactions of neutrinos with other particles. These detectors would need to be incredibly sensitive, capable of detecting even the faintest traces of tachyonic neutrinos as they pass through the Earth. Some experiments might even attempt to measure the effects of tachyonic neutrinos on the cosmic microwave background radiation, the faint glow left over from the Big Bang, to see if they leave any detectable signature. Another intriguing possibility is that tachyonic neutrinos could be detected indirectly by observing their effects on the large-scale structure of the universe. Neutrinos, both ordinary and tachyonic, are thought to have played a role in shaping the formation of galaxies and other cosmic structures. By studying the distribution of galaxies and the behavior of dark matter, scientists could potentially infer the existence of tachyonic neutrinos based on the way they interact with the fabric of the universe. The possibility that tachyonic neutrinos could be linked to dark matter is especially exciting. Dark matter is a mysterious substance that makes up about 27% of the universe's total mass, yet it cannot be directly observed because it does not emit light or interact with electromagnetic radiation. Instead, scientists infer its presence from its gravitational effects on visible matter. Some theories propose that dark matter is composed of weakly interacting particles, similar to neutrinos, but with properties that are still poorly understood. If tachyonic neutrinos do exist, they could potentially be a form of dark matter. Their ability to travel faster than light might make them an ideal candidate for the elusive substance that accounts for the missing mass in the universe. In this case, detecting tachyonic neutrinos could not only deepen our understanding of particle physics but also shed light on one of the most profound mysteries of the cosmos: the nature of dark matter. As scientists continue to explore the possibility of tachyonic neutrinos, they are also grappling with the broader philosophical implications of their potential existence. If particles that travel faster than light can exist, what does this mean for our understanding of the universe? Does it suggest that our current models of physics are incomplete, or is it possible that the laws of physics are far more flexible and nuanced than we realize? The search for tachyonic neutrinos is not just about finding a new type of particle. It is about pushing the boundaries of human knowledge and exploring the fundamental questions that have puzzled us for centuries. What is the nature of reality? What are the limits of the physical laws that govern the universe? And perhaps most profoundly, how can we unlock the secrets of the cosmos to better understand our place within it? As we continue to advance our scientific understanding and develop new technologies, the possibility of discovering tachyonic neutrinos remains a tantalizing and compelling mystery. Whether they exist or not, the pursuit of these particles will undoubtedly continue to drive innovation in physics, cosmology, and technology for generations to come. The search for tachyonic neutrinos is a journey into the unknown, one that could ultimately reshape our understanding of the universe and open new doors to previously unimaginable discoveries. Whether or not they are discovered in the coming years, their theoretical existence will continue to inspire scientists, philosophers, and dreamers alike to push the boundaries of what we know and to explore the deepest mysteries of the cosmos. Some physicists have proposed that the presence of tachyons could imply a form of retrocausality, in which events in the future could influence events in the past. While this notion sounds like the domain of science fiction, it is taken seriously in certain interpretations of quantum mechanics, and tachyonic neutrinos might offer a real-world avenue to investigate it. In quantum theory, retrocausality is sometimes proposed to explain entanglement, where two particles seem to instantaneously affect each other's state regardless of the distance separating them. This behavior, which Einstein famously referred to as spooky action at a distance, has been confirmed experimentally, though it still defies classical explanations. If tachyonic neutrinos can transmit information faster than light, they might provide a physical mechanism behind this bizarre quantum connection. Moreover, the existence of tachyonic neutrinos would not just be an exotic anomaly but would likely point toward a deeper and more complete layer of physical law. It may suggest that our current models are merely effective theories, useful for predicting outcomes within a limited domain, but ultimately incomplete. Just as Newtonian physics was superseded by Einstein's relativity, which in turn was supplemented by quantum mechanics, a new framework could be on the horizon, one in which tachyons and superluminal phenomena are not violations of nature's laws, but natural consequences of a higher-order structure. This possibility is precisely what excites many theoretical physicists. Tachyonic neutrinos could serve as messengers from this deeper layer of reality. Their properties, mass, speed, interaction cross-sections, and decay modes, could contain subtle fingerprints of new physics, much like the behavior of the Higgs boson confirmed the electroweak unification. If studied in enough detail, tachyonic neutrinos might lead us to new forces, new symmetries, or even extra dimensions curled up within the fabric of spacetime. In theoretical physics, tachyons are associated with imaginary mass, a term which doesn't mean fictional or non-existent, but rather refers to a mass squared value that is negative. In relativity, a particle's mass squared is used in equations that describe its energy and momentum. If the mass squared is negative, the result is an imaginary number when square-rooted, which defies classical physical interpretation. This mathematical oddity is precisely what defines a tachyon and distinguishes it from all known standard particles. Rather than traveling below the speed of light, tachyons must travel faster than light to remain consistent within the framework of special relativity. But there's a deeper nuance to the term: imaginary mass. When we speak of a particle with imaginary mass, we are essentially dealing with a system that destabilizes the quantum vacuum. In quantum field theory, the presence of a negative mass squared term in the Lagrangian of a field signals instability, a signal that the vacuum is not in its true lowest energy state. This condition isn't necessarily a bad thing. In fact, it's a mechanism behind the Higgs field and spontaneous symmetry breaking. That suggests that tachyonic behavior might not be pathological, but rather a sign that something deeper and more stable lies beneath the current field configuration. This leads to an interesting possibility. Perhaps neutrinos are not tachyonic all the time, but under certain conditions they behave as if they are. For instance, it's conceivable that in regions of spacetime with high curvature, like those near black holes or during the early universe, neutrinos could temporarily acquire tachyonic properties. In such cases, we wouldn't necessarily be dealing with particles that always move faster than light, but rather particles that are permitted to explore that regime under certain quantum conditions. There's also the question of Lorentz invariance, a foundational principle in physics stating that the laws of nature are the same for all observers, regardless of their constant velocity. If tachyonic neutrinos exist, they might violate Lorentz invariance, which would be a groundbreaking revelation. Many experiments, such as those conducted at CERN and Fermilab, have placed tight bounds on Lorentz violating parameters, but these bounds don't necessarily rule out tiny violations. If neutrinos have a tiny tachyonic component, it might be enough to signal Lorentz violation without clashing with current experimental data. Some models even attempt to reconcile tachyonic behavior with Lorentz invariance by introducing preferred frames of reference, cosmic, rest frames, relative to the background structure of spacetime. These ideas suggest that there may be a hidden ether-like substance, not in the outdated classical sense, but as a quantum background field that defines a universal frame. In such a framework, tachyons could move consistently and causally, but only relative to that preferred frame. This wouldn't restore Newtonian mechanics, but it would redefine what symmetry means in quantum gravity or string theory contexts. From an observational standpoint, one of the most dramatic moments in recent history that brought the idea of faster-than-light neutrinos to public attention was the 2011 Opera experiment. Scientists at the Gran Sasso Laboratory in Italy believed they had measured muon neutrinos traveling faster than the speed of light from CERN in Switzerland. For a brief moment, the scientific world was thrown into chaos. News headlines around the world proclaimed that Einstein might have been wrong. The implications were enormous. If neutrinos could break the light-speed barrier, they might be tachyons. However, after months of scrutiny, it was discovered that a loose fiber optic cable had skewed the timing measurements. Once the error was corrected, the data no longer supported superluminal travel. While disappointing to some, the episode had a silver lining. It revived interest in the possibility of exotic neutrino properties and inspired new theoretical investigations. Importantly, it also revealed how closely the scientific community watches for cracks in established paradigms, and how ready we are to explore the extraordinary when given evidence. Even with that result retracted, the idea didn't die. Theoretical models have since continued to entertain the possibility of tachyonic neutrinos, particularly in the context of dark matter and dark energy. Some speculative models propose that tachyonic neutrinos could act as mediators or hidden participants in the dark sector. Because neutrinos interact so weakly with ordinary matter, they make ideal candidates for slipping in and out of this hidden realm, and their potential superluminal speeds would make them uniquely suited to connect distant regions of space rapidly, potentially influencing the evolution of cosmic structure. There's even a philosophical dimension to tachyonic neutrinos. If they exist, they could call into question our deepest assumptions about determinism, locality, and even the direction of information flow. What would it mean if the universe were littered with particles that transmit signals backward in time? Could our own consciousness, bounded by causality, ever comprehend such events? And would it be possible, even in principle, to harness tachions for practical use, such as faster-than-light communication or even time travel? To date, we have no direct evidence for tachyonic particles, but the mere mathematical and conceptual framework supporting them keeps theorists engaged. Some speculate that neutrino oscillations, which are still not fully understood, might hide a tachyonic component. Since neutrinos change flavors as they travel through space, and since they do so in ways that don't always align with classical expectations, it's plausible that a more exotic mechanism is at play. Perhaps the very nature of oscillation itself hints at movement through a non-Euclidean spacetime, or the influence of unknown quantum fields. Another exciting frontier is the use of neutrinos in astronomical observation, known as neutrino astronomy. This emerging field uses high-energy neutrinos to probe the most distant and energetic processes in the universe, such as supernovae, gamma-ray bursts, and active galactic nuclei. Because neutrinos are unaffected by magnetic fields and pass through most matter unimpeded, they arrive at detectors like IceCube in Antarctica largely unchanged. If we ever detect a consistent discrepancy between the arrival times of neutrinos and photons from distant cosmic events, it might hint at faster-than-light propagation, or at least open the door for a deeper analysis of neutrino behavior. Even in the lab, high-precision neutrino experiments like Carlsruhe tritium neutrino experiment, are inching closer to unraveling the mystery of neutrino mass. While Cochrane is not designed to test for tachyonic properties directly, any unexpected results in the mass-squared measurements could point to something anomalous. If the measured value were ever to go negative consistently, it might be the first experimental evidence supporting the tachyonic neutrino hypothesis. In such cases, we wouldn't be dealing with a permanently superluminal particle, but with one that exists in a dynamic state, crossing in and out of tachyonic regimes depending on environmental conditions. This concept ties into the broader field of quantum gravity and variable spacetime metrics, where constants we assume to be universal, like the speed of light or the neutrino mass, might not be truly fixed across all frames or epochs. It forces us to question the rigidity of what we think are unchanging laws and instead adopt a more flexible, field-dependent view of the universe. Consider, for example, the potential implications in cosmology. If neutrinos were tachyonic during the earliest moments after the Big Bang, they could have traveled faster than light at a time when the universe was still smoothing out its structure. This superluminal behavior might have played a hidden role in cosmic inflation, or in establishing large-scale uniformity in the observable universe. Standard cosmology uses inflation to explain these phenomena, but tachyonic neutrinos could offer a new layer to that explanation, one involving particle dynamics rather than just scalar field expansion. Another angle to examine is the notion of phase transitions in the early universe. During cosmic phase changes, such as the separation of the electromagnetic and weak nuclear forces, fields underwent radical shifts in configuration. These transitions often introduce temporary instabilities in various particle fields. A neutrino field undergoing such a shift might briefly allow for tachyonic modes to manifest. This could result in exotic phenomena like faster-than-light bursts, tunneling effects, or even information transmission across large distances in early cosmic time. From a particle physics standpoint, investigating this would require extremely precise data. Neutrino observatories like Supercameo-Candy, IceCube, and future experiments such as Dune are increasingly sensitive to timing and energy anomalies. A key challenge is differentiating a genuine tachyonic signature from noise or experimental error. A slight discrepancy in neutrino arrival times, especially in relation to light or gravitational wave signals, could indicate the presence of a tachyonic state, but it must be scrutinized beyond any doubt. There have already been a few tantalizing hints. In 2011, the Opera experiment reported faster-than-light neutrino results. Though later attributed to a faulty timing cable, the incident opened the scientific imagination. What if that anomaly hadn't been an error? What if there are real cases, scattered across vast datasets, where neutrinos briefly exhibited superluminal velocities, but were dismissed due to assumptions about what was possible? It raises the broader question: how many miracles are missed because they fall outside our theoretical comfort zone? Moreover, the behavior of tachyonic neutrinos could redefine our approach to quantum communication and information theory. If superluminal neutrinos can indeed carry information, they could upend the concept of causality and make room for new types of messaging systems, potentially even unlocking forms of communication that are instantaneous or retrocausal. The possibility might sound far-fetched, but remember that quantum entanglement, too, once seemed like a mathematical oddity rather than a physical reality. Furthermore, this touches on the principle of Lorentz invariance, one of the cornerstones of special relativity. Tachyons appear to violate Lorentz invariance because their speed would exceed the ultimate limit defined by light. However, some modified theories of relativity, such as doubly special relativity, or those involving extra dimensions, allow for limited Lorentz violating scenarios. In such frameworks, tachyons and superluminal particles might exist without creating paradoxes or mathematical singularities. It's possible that our current formulation of symmetry in physics is a low-energy approximation, and that at higher scales, the symmetry breaks in subtle, tachyon-friendly ways. The consequences for string theory and higher-dimensional models are equally compelling. In some versions of string theory, tachyonic states naturally appear in the spectrum of possible vibrations. While these are usually interpreted as signals that a string vacuum is unstable, some theorists suggest that not all tachyons must decay. Some might stabilize in new vacua, creating entire branches of reality governed by different physical laws. Neutrinos with tachyonic tendencies could be remnants or echoes of such transitions, giving us a window into unseen regions of the string landscape. From the perspective of the Standard Model, a tachyonic neutrino doesn't easily fit. The model is built upon particles with real, positive mass terms. However, the discovery of neutrino mass already required extending the Standard Model. The concept of right-handed or sterile neutrinos was introduced to accommodate this fact, and those particles are themselves elusive, weakly interacting, and possibly massive. If sterile neutrinos exist, could they be tachyonic? Could this explain why they've been so difficult to detect? That idea opens a new theoretical avenue. What if all observed neutrinos are mixtures, quantum superpositions, of tachyonic and tachionic, slower-than-light states? This is not entirely without precedent. Neutrino oscillations already showed that flavor states are superpositions of mass states. The idea of extending this to superluminal components could mean that tachyonic behavior is not a separate identity, but a phase within a broader, more complex wave function. In this context, the role of decoherence becomes crucial. As neutrinos propagate over cosmic distances, interactions with quantum fields and virtual particles could collapse them into observable, subliminal states. The superluminal component might exist only briefly or under very specific conditions, almost like a fleeting phase of a quantum system. Such a framework would explain why we haven't seen unequivocal evidence of faster-than-light travel, yet still allows it to exist beneath the surface of standard physics. In fact, past experiments like Opera briefly suggested neutrinos might be arriving faster than light, sparking a wave of theoretical speculation before instrumental error was revealed as the true cause. But the public reaction to Opera revealed something deeper. A widespread willingness among both physicists and enthusiasts to entertain the possibility that our most cherished laws might not be as ironclad as we think. Even though the result turned out to be a miscalibration of a GPS system, it opened the door to renewed interest in exotic physics and reinforced the importance of testing boundaries. This brings us to the notion of falsifiability. One of the reasons tachyonic neutrino theories remain on the fringes of mainstream physics is their resistance to definitive falsification. If a theory can explain any anomaly post hoc by invoking a hidden faster-than-light behavior, it risks being unfalsifiable, and thus unscientific by traditional standards. But careful modeling and well-designed experiments can change that. By proposing specific, testable predictions, such as precise oscillation patterns that deviate under high-energy conditions or shifts in interaction rates with known particles, tachyonic models can begin to solidify their footing in empirical science. Another angle to consider is the role of neutrino oscillations. The discovery that neutrinos oscillate between flavors implies that they must have mass, contradicting the earlier belief that they were massless. But this opens a curious door. What if some of that mass is complex, partly real and partly imaginary? In other words, could neutrino oscillations involve a tachyonic component embedded within an otherwise real mass system? If so, the oscillation behavior itself could carry the imprint of superluminal mechanics, buried within quantum interference effects that we have yet to decipher. Moreover, it's worth reflecting on the broader metaphysical implications of tachyonic neutrinos. If such particles exist and truly move faster than light, they could, in theory, send signals backward in time. This opens a can of philosophical and physical worms, particularly concerning causality. If information can travel backward, what stops someone from altering the past? To date, most physicists agree that some mechanism, possibly tied to the consistency constraints of quantum mechanics, must forbid paradoxes. But even if time travel per se remains impossible, the existence of tachions might imply that causality is more flexible than we currently believe. This aligns with recent developments in the study of retrocausality. In quantum mechanics, certain interpretations, such as the two-state vector formalism, suggest that events in the future can influence the past. While still controversial, these ideas gain additional weight in a universe where faster-than-light particles exist. Could a tachyonic neutrino model give support to retrocausal interpretations of quantum physics? Could entanglement and non-locality be manifestations of subtle tachyonic exchanges beyond our current resolution? Even in technological terms, the stakes are high. If tachyonic neutrinos exist and we learn to detect or even manipulate them, the potential for revolutionary communication systems arises. Imagine devices capable of sending information through spacetime using particles that arrived before they were sent. Such technology would not only upend telecommunications but could give rise to forms of computation, encryption, and synchronization unimaginable with today's methods. However, the ethical and safety considerations of such breakthroughs would be immense. What are the implications of breaking causality? Then there's the intriguing question of the neutrino's identity within the Standard Model. Neutrinos are unique in that they only interact via the weak nuclear force and gravity, making them incredibly elusive. Their flavor, oscillation, and near-massless nature have puzzled physicists for decades. If the tachyonic hypothesis is true, it may suggest that the neutrino is not a mere Standard Model outlier but a window into a hidden layer of physics. Perhaps they are the emissaries of an alternate framework, one in which time, speed, and interaction are fluid variables, not constants. In this context, supersymmetry, SUSY, may play a vital role. SUSY theories propose that every standard particle has a heavier superpartner. If tachyonic neutrinos exist, might they be linked to these superpartners? Some SUSY variants predict particles with properties that border on tachyonic under certain conditions. Perhaps these conditions are not rare but merely hidden behind energy thresholds we've yet to cross. Neutrinos might then be a bridge, not just between lepton flavors, but between standard and supersymmetric realms. Likewise, string theory provides fertile ground for tachyonic speculation. In some formulations, tachyons appear as natural excitations of unstable string states. These aren't considered mistakes but rather indicators of phase transitions within the string vacuum. If neutrinos are connected to such strings, their tachyonic behavior could be a signpost of dimensional flux, shifts between compactified dimensions or transitions between stable string vacua. Understanding this link could finally provide experimental traction to a theory that has, for decades, struggled to find direct testability. One cannot ignore the gravitational angle either. Neutrinos, despite their ghostly nature, carry mass and energy, and thus are subject to gravity. But how do tachyonic particles interact with curved spacetime? General relativity does not currently accommodate faster-than-light travel in a straightforward way, but some modified gravity theories do. For instance, certain Lorentz-violating models or emergent gravity frameworks allow for exotic trajectories that bypass traditional light speed barriers. Could neutrinos be slipping through these cracks, following paths that skirt the limits of known geometry? There is the possibility that our entire framework of physics is only a low-energy approximation of a deeper, hidden order. Tachyonic neutrinos might be ordinary particles from the perspective of a higher-dimensional theory, a realm in which speed, as we define it, is meaningless or reinterpreted entirely. Our instruments, rooted in four-dimensional spacetime, may only catch glimpses of these entities, distorted through the lens of our limited perception. If we ever hope to understand tachyons, neutrinos or otherwise, we may have to abandon more than just the speed limit of light. We may have to rewire our understanding of reality itself. As we venture deeper into the theoretical implications of tachyonic neutrinos, we also find ourselves contemplating a new era of particle physics, one that stretches far beyond what we have traditionally defined as the known universe. The pursuit of tachyonic neutrinos, if anything, underscores the limitations of our present understanding. Our current models of physics are grounded in a framework where the speed of light acts as a universal constant. Yet tachyons challenge this assumption, suggesting that there could be realms of existence where faster-than-light particles are the norm, not the exception. This realization forces us to reconsider our entire conception of the cosmos. The study of tachyonic neutrinos also holds the potential to change how we view the early universe. During the first few moments after the Big Bang, the universe was a chaotic and extremely high-energy environment. It's theorized that during this period, the laws of physics as we know them may have behaved differently, with particles and forces interacting in ways that we can only speculate about. Could the existence of tachyonic neutrinos be a leftover remnant from this early phase of the universe? Could they be the echoes of a time before the universe settled into the familiar framework we see today? Some cosmologists even argue that understanding the potential behavior of tachyonic neutrinos could provide insights into the formation of dark matter. After all, one of the biggest mysteries in modern physics is the nature of dark matter. It doesn't interact with light, making it nearly impossible to detect directly, yet it exerts gravitational effects on visible matter. Could tachyonic neutrinos, in some way, contribute to the unseen mass of the universe? Are they the elusive, dark, particles that influence cosmic structure, or are they something else entirely, a bridge between ordinary and dark matter? Another fascinating aspect is how tachyonic neutrinos could be tied to the concept of symmetry breaking in particle physics. Symmetry breaking refers to the phenomenon where the laws of physics seem to change at different energy scales. In high-energy environments, symmetries that govern particle interactions can be broken, leading to the emergence of new particles and forces. The tachyonic neutrino could potentially represent a unique case of symmetry breaking, a particle that only manifests under extreme conditions, much like how the Higgs boson emerged in high-energy collisions. Understanding this phenomenon could unlock new fields of research, especially in the search for a grand unified theory, GUT, that ties together all fundamental forces. Furthermore, the search for tachyonic neutrinos could reshape the very nature of experimentation in particle physics. Currently, the Large Hadron Collider, LHC, is the centerpiece of high-energy physics research. However, if tachyonic neutrinos do indeed exist, the standard approaches to particle detection might be inadequate. These particles move faster than light, making them incredibly difficult to detect using current methods. As such, the scientific community may need to develop entirely new detection techniques, perhaps involving space-based telescopes or deep underground laboratories, where neutrinos can be studied in isolation from the interference of other cosmic phenomena. This also brings us to a highly speculative but intriguing thought, the idea that tachyonic neutrinos might one day play a role in practical technologies. If scientists could develop methods to control or manipulate tachyonic particles, this could lead to breakthroughs far beyond our current capabilities. One possibility is the development of super-efficient propulsion systems. Imagine spacecraft capable of traveling faster than light by harnessing tachyonic neutrinos, or even new methods of energy production that rely on these elusive particles. Such advances could forever change the way we approach space travel, energy generation, and many other fields. However, the very nature of these particles presents significant challenges. If tachyonic neutrinos truly do exist, it's possible that their behavior could be governed by a set of laws far more complex than what we understand today. In particular, their potential ability to interact with other particles in non-traditional ways could present obstacles that we are not yet equipped to handle. To fully comprehend tachyonic neutrinos, we would need to extend our understanding of quantum mechanics and general relativity, both of which are not yet compatible with one another at the highest energies. This would likely require new mathematical frameworks, potentially blending quantum field theory and a more unified model of gravity. Moreover, there are still fundamental questions surrounding the potential energy states of tachyonic neutrinos. In theoretical models, tachyons typically represent particles that have an imaginary mass. But what does that actually mean in physical terms? How does a particle with an imaginary mass behave in a universe governed by real mass and energy? And what does this imply for the conservation laws we hold so dearly? Could a tachyonic neutrino somehow escape the constraints of energy conservation, violating one of the bedrock principles of modern physics? While this may sound speculative, it's precisely these kinds of questions that drive us toward new realms of discovery. Interestingly, these challenges may not just be theoretical. In fact, a number of researchers are already experimenting with techniques that could potentially provide answers to some of these questions. From creating extreme environments in particle accelerators to studying cosmic ray interactions in space, scientists are exploring every avenue in hopes of uncovering the truth behind tachyonic neutrinos. However, given the current limitations of our experimental tools, it is likely that this search will continue for decades, with new generations of physicists taking up the mantle of exploration. At the same time, the search for tachyonic neutrinos also holds profound philosophical implications. If we were to discover that such particles exist, it would force us to reconsider our place in the universe. The nature of time, causality, and reality itself could all be called into question. The discovery of faster-than-light particles could be seen as a fundamental shift in the way we perceive the fabric of the universe. It would challenge the very essence of what we understand about cause and effect, potentially leading to new insights into the nature of reality itself. The concept of tachyonic neutrinos is one of the most exciting and perplexing ideas in modern physics. While still purely theoretical, their potential to revolutionize our understanding of the universe is immense. Whether they are a window into a new realm of physics, a clue to the mysteries of dark matter, or a technological breakthrough waiting to happen, the hunt for tachyonic neutrinos could shape the future of science in profound ways. Only time will tell if we will one day uncover the truth about these elusive particles. However, the journey itself promises to be one of the most fascinating scientific quests of our time. As we continue to explore the potential of tachyonic neutrinos, we must also consider the broader implications they might have on the future of physics and technology. If tachyonic neutrinos are proven to exist, they could potentially offer answers to some of the most elusive and complex problems that have puzzled scientists for centuries. Their unique properties, moving faster than light, having a mysterious connection to the nature of time, and possibly linking us to realms beyond the observable universe, could reshape the landscape of particle physics in ways we cannot yet fully grasp. One of the more speculative yet fascinating avenues of study lies in the relationship between tachyonic neutrinos and the fabric of spacetime itself. General relativity, which governs the gravitational forces in the universe, is based on the idea that mass and energy warp spacetime, creating what we perceive as gravity. But if tachyonic neutrinos exist and possess mass or energy in a way that defies the usual rules, could they alter spacetime in ways we haven't imagined? Could they provide us with clues to understanding the so-called quantum gravity that has eluded scientists for decades? This could lead to new breakthroughs in unifying the forces of nature, gravitational, electromagnetic, weak, and strong, into a single, cohesive framework, much like how the standard model of particle physics successfully unifies three of these forces. Moreover, if tachyonic neutrinos are indeed faster than light particles, this could open up entirely new ways to think about space and time. Right now, the speed of light sets a hard limit on how fast information or matter can travel, fundamentally influencing how we understand causality. But if tachyonic neutrinos can exist and travel at faster than light speeds, they could potentially be used to send information or particles across vast distances instantaneously, bypassing the limitations imposed by light speed travel. This could lead to advances in communications technology, possibly enabling faster-than-light communication systems, a concept that, while once relegated to science fiction, might not be entirely out of reach with the discovery of tachyonic neutrinos. The potential for faster-than-light communication could have profound impacts on how we interact with the universe. Imagine a future where spacecraft are able to communicate across vast interstellar distances, or where we can send information between Earth and colonies on distant planets almost instantly. While such technology remains speculative, the discovery of tachyonic neutrinos could provide the foundation for developing new, more efficient methods of communication that fundamentally change our approach to space exploration and even our daily lives. Tachyonic neutrinos also offer an exciting challenge to one of the most well-established principles of modern physics: the speed of light as the universal speed limit. The speed of light has long been seen as a fundamental constant of nature, a boundary beyond which nothing can travel. This idea is central to our understanding of relativity and causality. But the theoretical existence of particles that can exceed the speed of light opens up a Pandora's box of possibilities. What would happen to our understanding of relativity if tachyonic neutrinos were proven to exist? Would the very structure of space-time itself be called into question? Could we one day unlock the secrets of wormholes, time travel, or other exotic phenomena that are currently the stuff of theoretical physics? The introduction of faster-than-light particles into the realm of physics could also trigger a re-evaluation of our entire understanding of cosmology. Theoretical models of the universe, such as those based on string theory or loop quantum gravity, could be significantly altered if we find evidence that particles like tachyonic neutrinos exist. It's possible that the discovery of such particles could provide new insights into the mysteries of dark matter and dark energy, which together make up the majority of the universe's mass and energy content. While these phenomena are still largely theoretical, the existence of tachyonic neutrinos might provide new tools for uncovering their true nature. In terms of practical applications, the existence of tachyonic neutrinos could lead to a revolution in energy production. Neutrinos are already known to interact weakly with matter, which means they can pass through large amounts of material without being absorbed or deflected. If tachyonic neutrinos could be harnessed in a controlled manner, they might offer a new way to generate energy without the waste or radiation associated with traditional energy sources. This could be the key to unlocking a new, clean source of energy that doesn't rely on fossil fuels or nuclear reactions. While this is speculative, the sheer novelty of tachyonic neutrinos could inspire a new era of energy research. Additionally, the discovery of tachyonic neutrinos could have profound implications for the study of fundamental forces in nature. Currently, the forces of electromagnetism, gravity, the strong nuclear force, and the weak nuclear force are treated separately, though efforts like string theory aim to unify them into a single framework. If tachyonic neutrinos can be shown to interact with these forces in unexpected ways, it could provide the missing piece of the puzzle, shedding light on how all forces in the universe might be connected. The unification of forces has been a long-standing goal of physicists, and tachyonic neutrinos could play a crucial role in this endeavor. In the broader context of scientific progress, the search for tachyonic neutrinos represents a bold step forward in our understanding of the universe. The scientific community has long relied on the development of new theories and experiments to push the boundaries of knowledge, and the potential discovery of tachyonic particles would be no exception. The challenges in detecting these elusive particles, as well as the philosophical and practical questions they raise, make them a truly fascinating area of study. If we can overcome the difficulties in detecting them, we might find ourselves on the cusp of a new era in physics, one that could completely transform our understanding of the fundamental nature of reality. But with all these exciting possibilities come risks and uncertainties. The discovery of tachyonic neutrinos could challenge the very foundations of science, calling into question not just our understanding of physics but the way we approach scientific inquiry itself. As we venture deeper into the unknown, we must be prepared for the unexpected, knowing that each new discovery brings with it the potential for both breakthroughs and setbacks. Yet, it is this very uncertainty that drives the search for new knowledge and makes the pursuit of tachyonic neutrinos such an exciting and pivotal endeavor in the history of science. The exploration of tachyonic neutrinos is an intellectual journey that holds the potential to reshape our understanding of the universe. From revealing hidden truths about the early universe to offering potential breakthroughs in technology, energy, and communication, tachyonic neutrinos could be the key to unlocking a wealth of new discoveries. Whether or not they ultimately exist, the pursuit of these mysterious particles is certain to push the boundaries of scientific knowledge and open up new frontiers in the study of physics and cosmology. Only time will tell what the future holds for tachyonic neutrinos, but one thing is for certain: their potential to change the way we understand the universe is immeasurable. As we continue to explore the fascinating concept of tachyonic neutrinos, we find ourselves standing at the precipice of a potential paradigm shift in the way we view the universe. With each new breakthrough in particle physics, we have uncovered layers of reality that were once hidden from our comprehension. However, tachyonic neutrinos, if they exist, could unlock an entirely new dimension of understanding that stretches far beyond what we have been able to perceive through conventional means. For one, the discovery of tachyonic neutrinos could challenge the current interpretations of quantum mechanics. Quantum mechanics, as it stands, is a framework that governs the behavior of particles at the smallest scales. But one of the most perplexing aspects of quantum theory is the wave-particle duality, which suggests that particles like photons can exist as both particles and waves, depending on how they are observed. This strange behavior has already forced physicists to rethink our understanding of reality. Now, introducing tachyonic neutrinos into the mix could add yet another layer of complexity to this already perplexing theory. How would these faster-than-light particles interact with the quantum fields that govern the behavior of subatomic particles? Would they obey the same rules, or would they reveal an entirely new set of quantum principles that we have yet to discover? Moreover, tachyonic neutrinos could lead to new technologies that we can't yet fully imagine. The concept of harnessing faster-than-light particles for communication, energy generation, or even propulsion is still very much in the realm of speculation, but the implications are immense. Just as the discovery of electricity revolutionized the world centuries ago, the discovery of a practical application for tachyonic neutrinos could usher in a new age of technological innovation. These particles could potentially be used in energy transmission systems that do not rely on conventional means like electromagnetic waves or even gravitational fields. We might even imagine a scenario where spacecraft could use tachyonic neutrinos for propulsion, effectively bypassing the need for traditional fuel sources and allowing for interstellar travel at unimaginable speeds. In addition to their potential technological applications, tachyonic neutrinos could also have profound implications for our understanding of the cosmos itself. One of the most intriguing ideas to emerge from the study of these particles is their potential to help us solve some of the greatest mysteries in cosmology. For instance, they might provide a key to understanding dark matter and dark energy, two of the most mysterious and elusive substances in the universe. Despite making up roughly 95% of the universe's mass energy content, dark matter and dark energy remain largely invisible and undetectable by traditional means. If tachyonic neutrinos exist, their unique properties might allow them to interact with these invisible forces in ways that could reveal their true nature, offering a glimpse into the fabric of the cosmos that has long remained hidden from view. The connection between tachyonic neutrinos and dark matter is not purely speculative either. Some theories suggest that dark matter could be made up of particles that behave in ways similar to neutrinos, but with different properties. Tachyonic neutrinos, with their unique speed and interactions, could offer a new way to probe the nature of dark matter. If these particles can be detected or studied in greater detail, They could provide critical clues to the composition and behavior of dark matter, helping us to unlock the secrets of the universe's most elusive substances. Another area where tachyonic neutrinos could have an impact is in the study of time itself. Time is one of the most fundamental aspects of our existence, yet it remains one of the most enigmatic. For centuries, physicists have sought to understand the true nature of time, with theories ranging from the relativistic view of time as a fourth dimension to the idea that time is an emergent property of the universe. Tachyonic neutrinos, with their faster-than-light speeds, could provide a new perspective on the flow of time. Could these particles be connected to the flow of time in ways we have not yet understood? If tachyonic neutrinos travel faster than light, does that mean they exist outside of the conventional flow of time? These are questions that could fundamentally alter our perception of reality and challenge our most basic assumptions about the universe. Moreover, tachyonic neutrinos could offer a new way to explore the origins of the universe. According to some theories, the universe underwent a rapid expansion during the first few moments after the Big Bang, a process known as inflation. This expansion stretched the fabric of space-time to unimaginable proportions in a fraction of a second. If tachyonic neutrinos existed during this period, they could have played a role in shaping the early universe. They might have interacted with other fundamental forces in ways that influenced the development of the cosmos as we know it. By studying these particles, we could gain new insights into the processes that occurred during the infancy of the universe, potentially leading to a deeper understanding of its origins and evolution. On a more practical level, the potential to manipulate tachyonic neutrinos could open up entirely new fields of study in physics and engineering. One of the most exciting possibilities is the creation of advanced sensors and detectors capable of measuring these particles. Current neutrino detectors are incredibly sensitive, but they require enormous amounts of energy and sophisticated technology to function. If tachyonic neutrinos can be detected and studied in a controlled environment, it could lead to the development of new types of detectors with unprecedented sensitivity and accuracy. These could be used in a wide range of applications, from detecting hidden phenomena in space to monitoring the behavior of subatomic particles in laboratory experiments. Furthermore, tachyonic neutrinos could inspire new theories in other areas of physics, such as string theory or quantum field theory. String theory, in particular, has long sought to unify the fundamental forces of nature by postulating that the basic building blocks of reality are not particles, but tiny vibrating strings. The discovery of tachyonic neutrinos could offer a new avenue for testing these theories and refining our understanding of the universe. By studying the interactions between these particles and the forces of nature, we might uncover new principles that help to bridge the gap between the quantum world and the macroscopic world that we experience every day. In the realm of mathematics, the existence of tachyonic neutrinos could also provide new insights into the nature of space-time and the geometry of the universe. Theoretical models that describe the fabric of spacetime, such as those based on general relativity or quantum gravity, could be tested and refined through the study of these particles. Tachyonic neutrinos, with their ability to move faster than light, could offer a way to probe the structure of spacetime at the smallest scales, revealing new details about how the universe is organized at its most fundamental level. These mathematical models could lead to breakthroughs in our understanding of black holes, gravitational waves, and other phenomena that are governed by the laws of physics. The discovery of tachyonic neutrinos, however, is not without its challenges. As we have seen in our exploration of these particles, detecting and studying them is an immense scientific hurdle. Unlike other particles, neutrinos interact very weakly with matter, making them incredibly difficult to detect. To detect tachyonic neutrinos, scientists would need to develop new techniques and technologies that are far more advanced than what we currently have at our disposal. This task will require collaboration across multiple fields of research, including particle physics, cosmology, and advanced engineering. But if these particles are found, the potential rewards could be nothing short of transformative. Tachyonic neutrinos represent one of the most exciting and mysterious frontiers in modern physics. If they exist, these particles could offer a key to unlocking some of the deepest questions about the universe, from the nature of dark matter and dark energy to the very fabric of spacetime itself. Whether or not we ever detect tachyonic neutrinos, the search for these particles is bound to push the boundaries of our knowledge and inspire new ideas in the realms of science, technology, and philosophy. The journey to understand these elusive particles is just beginning, and with it comes the promise of discoveries that could redefine everything we know about the cosmos. Tachyonic neutrinos, in essence, represent an extraordinary realm of physics where our current laws and models break down or may need to be reimagined. As the scientific community delves deeper into the potential existence and implications of these particles, we might find that the very foundations of spacetime, quantum mechanics, and relativity require revision or expansion. The exploration of such particles challenges our understanding of the universe's structure and forces us to question the limits of the known laws of physics. One of the most intriguing aspects of tachyonic neutrinos lies in the paradox of their potential speeds. If they indeed travel faster than light, they could exist in what physicists call the causal order of time. This idea presents both a challenge and an opportunity for understanding how the fabric of reality works. In Einstein's theory of relativity, no particle can travel faster than light without breaking causality, the principle that cause must precede effect. This principle underpins much of classical physics, yet tachyonic neutrinos, if they exist, could throw this foundation into disarray. Could these particles really exist outside of the normal sequence of cause and effect? What would this mean for our understanding of time, space, and the relationship between the two? A critical question then emerges: if tachyonic neutrinos challenge the traditional causal structure of the universe, what does this imply for our understanding of the past, present, and future? Could the discovery of such particles lead to a deeper understanding of time travel, or even suggest that time itself might be more fluid than we have ever imagined? These speculative ideas bring us into the realm of theoretical physics, where time travel paradoxes and other mind-bending concepts have long been debated. While tachyonic neutrinos might not provide direct answers to these questions, their discovery would certainly open up new avenues of research that could eventually change our entire perspective on time and causality. One fascinating consequence of faster-than-light particles like tachyonic neutrinos is the potential for what is known as tachyonic fields. These fields, based on the properties of tachyons, could be theorized to exist across the universe, and studying them could lead to entirely new forms of interaction between matter and energy. Some physicists speculate that these fields could be linked to cosmic phenomena such as black holes, quasars, and other high-energy events, as well as the more mysterious aspects of the universe like dark energy and dark matter. If tachyonic neutrinos were found to be part of this field, it might explain how energy behaves in these extreme environments and provide new insights into the very fabric of space-time. Furthermore, the implications of tachyonic neutrinos extend beyond theoretical physics into areas like cosmology. The study of the early universe and the conditions present during the Big Bang is one of the most pressing questions for modern scientists. Tachyonic neutrinos, with their ability to travel faster than light, might offer a unique opportunity to understand the behavior of particles in the chaotic conditions of the universe's infancy. These particles could provide clues to how the fundamental forces we observe today were unified at the beginning of the cosmos, potentially offering a window into the earliest moments of creation. One of the key areas in which tachyonic neutrinos might play a role is in the search for a unified theory of everything. This theory, which seeks to reconcile the four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into one all-encompassing framework, remains one of the biggest challenges in theoretical physics. While we have made great strides in understanding these forces individually, a complete unification has eluded us. If tachyonic neutrinos exist, they could hold the key to bridging the gaps between quantum mechanics and general relativity, two theories that have traditionally been at odds with one another. These particles could serve as a crucial bridge in developing a more comprehensive theory that explains all of nature's forces in a single equation. Beyond the scientific community, the discovery of tachyonic neutrinos would have profound philosophical implications. Throughout human history, the pursuit of knowledge has been driven by the desire to understand the nature of reality, the universe, and our place within it. The existence of particles that defy conventional physics would challenge many of our basic assumptions about the world. Concepts like causality, the speed of light, and even the nature of time itself could no longer be taken for granted. If tachyonic neutrinos exist, they would force us to reconsider our very understanding of reality and ask fundamental questions about the limits of human knowledge and the scope of scientific inquiry. While the potential discovery of tachyonic neutrinos might seem like a distant, speculative idea, it's important to remember that scientific breakthroughs often begin with seemingly impossible or implausible ideas. Just as the discovery of quantum mechanics revolutionized our understanding of the microscopic world, and the theory of relativity challenged our perceptions of space and time, the discovery of tachyonic neutrinos could ultimately lead to a new era of scientific understanding. The road to uncovering the truth about these mysterious particles may be long and difficult, but it could also be the key to unlocking some of the universe's deepest secrets. In addition to the theoretical implications, there is also the possibility of practical applications that could arise from the study of tachyonic neutrinos. Just as the development of technologies like lasers, transistors, and quantum computers were once thought to be purely theoretical pursuits, so too could the study of faster-than-light particles lead to groundbreaking new technologies. For instance, if we could harness the properties of tachyonic neutrinos, we might develop new communication methods that transcend the limitations of current systems, potentially revolutionizing fields like telecommunications and information technology. Similarly, the energy potential of tachyonic neutrinos, if it could be tapped into, might offer a new source of power that could change the way we generate and consume energy. The implications of tachyonic neutrinos also stretch into the realm of space exploration. While interstellar travel may seem like the stuff of science fiction, faster-than-light particles could provide the key to making such journeys a reality. If we could develop technology that utilizes tachyonic neutrinos for propulsion or communication, it might allow us to explore distant star systems and galaxies far beyond the reach of current spacecraft. This could usher in a new era of space exploration, allowing humanity to become a truly interstellar species. The search for tachyonic neutrinos, therefore, represents not only a scientific quest but also a journey that could change the trajectory of human progress. Whether or not these particles exist, the pursuit of understanding them will undoubtedly lead to new discoveries and technologies that will shape the future in ways we can't yet fully predict. Just as the search for the Higgs boson and gravitational waves led to revolutionary breakthroughs, so too could the study of tachyonic neutrinos pave the way for a new understanding of the universe and our place within it. Ultimately, the question of whether tachyonic neutrinos exist is one that may take decades or even centuries to answer. The technology and understanding required to detect these particles are still in their infancy, and much work remains to be done. But as scientists continue to probe the mysteries of the universe, the possibility of finding these elusive particles is an exciting and tantalizing prospect that could redefine everything we know about physics, space, and time. The journey into the realm of tachyonic neutrinos is just beginning, and its discoveries could change the course of human history forever. As we continue exploring the theoretical underpinnings of tachyonic neutrinos, one of the key areas to consider is the role of quantum mechanics in their potential existence. Quantum mechanics, with its strange and counterintuitive nature, often challenges the way we think about the physical world. The discovery of tachyonic neutrinos could take quantum theory to its limits, pushing the boundaries of what is considered possible in the realm of subatomic particles. One important concept to examine here is the idea of quantum fields. In quantum field theory, particles are seen not as isolated entities but as excitations or ripples in underlying fields. If tachyonic neutrinos exist, they might be considered as excitations in a tachyonic field, one that operates outside the usual constraints of relativistic physics. This field could potentially be connected to the Higgs field, which plays a central role in giving particles their mass. By extending this idea, one could hypothesize that tachyonic neutrinos, if they exist, would interact with the Higgs field in a fundamentally different way than regular neutrinos, possibly explaining their faster-than-light behavior. However, this raises further questions. what kind of mathematical framework could describe tachyonic neutrinos? Current models based on quantum field theory and relativity might not be able to fully accommodate the possibility of these particles. Physicists would have to develop entirely new models that can incorporate tachyonic neutrinos and their associated fields. This is no small task, as it would require rethinking the very fabric of spacetime itself. The equations we use to describe the universe might need to be restructured, incorporating new terms and principles to account for the unique properties of tachyonic particles. Another fascinating possibility is that tachyonic neutrinos could shed light on the mysterious nature of dark matter and dark energy. These two phenomena have been among the most elusive and difficult to understand in modern physics. Together, they make up around 95% of the universe's mass-energy content, yet we have little understanding of what they actually are. Some theorists speculate that tachyonic neutrinos could be linked to these dark components of the universe. If tachyonic neutrinos interact with dark matter or dark energy in ways we don't yet understand, they could help us unlock the secrets of these cosmic mysteries. The connection between tachyonic neutrinos and the elusive properties of dark energy and dark matter could be explored through high-energy experiments. One avenue of research might involve the study of cosmic rays, high-energy particles from space that reach Earth. If tachyonic neutrinos are indeed traveling faster than light, they could potentially be detected as part of the cosmic rays spectrum. Similarly, the study of cosmic microwave background radiation, CMB, the afterglow of the Big Bang, could reveal clues about how tachyonic particles may have influenced the early universe. Understanding the relationship between tachyonic neutrinos and dark matter could ultimately lead to a breakthrough in our understanding of the cosmos and the forces that govern its evolution. Moreover, if tachyonic neutrinos are shown to exist, their discovery might fundamentally alter our understanding of the Standard Model of particle physics. The Standard Model, which has been the cornerstone of particle physics for decades, describes the known elementary particles and their interactions. However, it has significant gaps, such as the absence of a description for gravity or the nature of dark matter. The addition of tachyonic neutrinos to the Standard Model would challenge the model's completeness, potentially leading to the development of a more comprehensive theory of everything. This might include the unification of all fundamental forces, including gravity, and the establishment of new particle categories that we have yet to fully comprehend. This would also introduce a significant shift in the way we think about the universe's fundamental laws. The discovery of tachyonic neutrinos could potentially lead to a paradigm shift similar to the one caused by the discovery of quantum mechanics, or the theory of relativity. As scientists begin to understand more about these particles and their behavior, we could see a dramatic transformation in our approach to theoretical physics. Ideas that were once relegated to the realm of science fiction, such as faster-than-light travel, time manipulation, or even the possibility of parallel universes, might no longer seem so far-fetched. The study of tachyonic neutrinos could also have profound implications for the future of technology. While we are still far from fully understanding these particles, even the pursuit of this knowledge could lead to groundbreaking innovations. For example, if we can find a way to detect and manipulate tachyonic neutrinos, it might open up entirely new avenues for energy generation or communication. The possibility of harnessing faster-than-light particles could revolutionize our understanding of propulsion systems, potentially enabling interstellar travel. This could have profound implications not just for space exploration, but for the future of human civilization as a whole. Yet, as with all scientific pursuits, the discovery of tachyonic neutrinos would not be without its challenges. Detecting these particles would be incredibly difficult, given their elusive nature and the fact that they would travel faster than light. Current technology might not be sufficient to capture such particles, so scientists would need to develop new detectors and techniques to observe them. Theoretical models would also need to be refined and tested rigorously before they could be accepted as valid. And even if tachyonic neutrinos are discovered, it would take years, if not decades, to fully understand their properties and implications. This brings us to the question of how we would verify the existence of tachyonic neutrinos in the first place. If they truly travel faster than light, they would not behave in the same way as regular neutrinos, which are known to travel at speeds close to the speed of light. One potential method of detection could involve studying the behavior of neutrinos and particle accelerators, where scientists could look for signs of tachyonic particles exhibiting unusual properties. Another approach could involve studying cosmic phenomena, such as supernovae or gamma-ray bursts, where high-energy neutrinos are generated. If tachyonic neutrinos are present in these events, they might leave distinctive signatures that could be detected with advanced telescopes and other instruments. There is the matter of the potential consequences of discovering tachyonic neutrinos. If they do exist, they could radically change how we understand the universe, forcing us to reconsider not only the laws of physics, but also the very nature of reality. Time travel, faster-than-light communication, and new forms of energy could all become possible if we are able to harness the properties of these particles. However, with such power comes responsibility, and the potential for unintended consequences would need to be carefully considered. The discovery of tachyonic neutrinos could mark the beginning of a new era in physics, one that challenges everything we thought we knew about the universe and our place in it. As the exploration of tachyonic neutrinos continues, it's important to delve deeper into the scientific implications and practical applications of their potential existence. If these particles truly exist and exhibit faster-than-light properties, it would imply that our current models of space-time and causality would need to be revised. One of the most profound consequences of this discovery could be a re-evaluation of the nature of time itself. In current physics, time is considered a linear progression from past to present to future, and this linearity is crucial to maintaining causality, the principle that cause precedes effect. However, if tachyonic neutrinos can move faster than light, they could challenge this fundamental principle. The speed of light has long been seen as a universal constant, serving as a cosmic speed limit for all particles and information. This limit is central to Einstein's theory of relativity, which governs the behavior of space and time. According to relativity, as objects approach the speed of light, their mass increases, and the time it takes for them to travel further becomes longer. This results in the famous time dilation effect, where time appears to slow down for an object moving at relativistic speeds. However, the introduction of tachyonic neutrinos, which may travel faster than light, could alter these relativistic effects. In this new framework, time might no longer be linear, and causality could be violated. What does it mean for causality to be violated? In simple terms, if information or particles can travel faster than light, it opens the door for scenarios where the effect precedes the cause, a situation often described as time travel. For example, a message sent via tachyonic neutrinos could theoretically arrive before the sender even transmitted it. This could lead to paradoxes where events unfold in reverse order, potentially violating the flow of time as we understand it. The implications for fundamental physics, as well as our perception of reality, would be vast and revolutionary. Moreover, the violation of causality might have consequences beyond the realm of theoretical physics. It could impact everything from the stability of the universe to the very way we perceive the passage of time. For instance, if tachyonic neutrinos interact with other particles in ways that create backward causality, it could disrupt the chain of events that lead to our current understanding of cause and effect. This could cause ripples throughout the laws of nature, affecting everything from the laws of thermodynamics to quantum mechanics. The ripple effect could even challenge the foundations of other scientific disciplines like chemistry and biology, which are based on predictable cause and effect relationships. In addition to the philosophical and theoretical implications, the discovery of tachyonic neutrinos would undoubtedly have profound technological consequences. The practical applications of faster-than-light particles could revolutionize numerous fields, from communication to transportation to energy production. For example, the ability to transmit information faster than light could pave the way for instantaneous communication across vast distances, rendering current communication technologies obsolete. In space exploration, tachyonic neutrinos might enable new propulsion methods, allowing spacecraft to travel at speeds previously thought impossible, drastically reducing travel times within our solar system and beyond. The energy production potential of tachyonic neutrinos could be equally transformative. If we could harness these particles, their faster-than-light properties could potentially be used to generate energy in ways that defy current technology. By capturing the energy from tachyonic neutrinos, scientists could explore new forms of energy generation that are not limited by the constraints of current power systems. This could lead to breakthroughs in sustainable energy production, providing a solution to the global energy crisis and reducing our reliance on fossil fuels. On the other hand, there are dangers associated with tampering with such a powerful phenomenon. The manipulation of tachyonic neutrinos and their faster-than-light capabilities could introduce unforeseen risks. For instance, creating artificial tachyonic fields or accelerating particles to such extreme speeds might result in uncontrollable energy releases or unintended consequences for spacetime itself. Such experimentation could disrupt the delicate balance of the universe, leading to unpredictable changes in fundamental physical constants, or even catastrophic consequences for the fabric of reality. The potential existence of tachyonic neutrinos also raises questions about the stability and structure of the universe. If faster-than-light particles are indeed a part of nature, they may play a critical role in the balance of forces that govern the cosmos. It's possible that they have been present since the beginning of the universe, potentially contributing to the cosmic inflation that occurred just after the Big Bang. In this case, understanding the behavior of tachyonic neutrinos could provide new insights into the origins of the universe, the formation of galaxies, and the evolution of cosmic structures over time. Moreover, the study of tachyonic neutrinos could help clarify the role of exotic particles in the universe, such as those associated with dark matter and dark energy. These elusive substances make up the vast majority of the universe's mass, yet their properties remain a mystery. Some theorists speculate that tachyonic particles might be linked to dark matter or dark energy in ways we don't yet understand. If this is true, then discovering tachyonic neutrinos could provide the key to unlocking the secrets of the dark universe, helping us to understand why galaxies move in the way they do and how the expansion of the universe is accelerating. The idea that tachyonic neutrinos could be tied to dark matter and dark energy is not far-fetched. After all, both dark matter and dark energy are invisible and difficult to detect, yet their effects are observable. Dark matter, for instance, exerts a gravitational pull on visible matter, influencing the motion of galaxies and clusters of galaxies. Dark energy, meanwhile, is thought to be responsible for the accelerated expansion of the universe. If tachyonic neutrinos interact with dark matter or dark energy in some way, they could provide a crucial link in our understanding of these mysterious substances. In the long run, the pursuit of tachyonic neutrinos could lead to new discoveries that reshape not only our understanding of physics, but also our place in the universe. These particles could act as a gateway to new realms of scientific inquiry, challenging existing theories and inspiring the development of innovative technologies. Whether or not tachyonic neutrinos exist, the search for them is an example of how scientific curiosity drives progress, pushing the boundaries of human knowledge and inspiring future generations to continue exploring the unknown. However, before any of this can become a reality, the existence of tachyonic neutrinos needs to be proven. This requires careful experimentation, the development of new detection technologies, and the formulation of new theoretical models that can account for the unique properties of these particles. If such a discovery is made, it will undoubtedly be one of the most significant milestones in the history of science. It will force us to rethink the very foundations of physics and open the door to a future where the laws of the universe are no longer confined by the constraints of relativistic physics. The search for tachyonic neutrinos is not only about understanding the nature of these elusive particles, but also about pushing the limits of human innovation in experimental physics. To detect such particles, scientists would need to devise entirely new methods of observation and measurement. Current technologies, such as particle accelerators and neutrino detectors, are designed to observe particles that move at or below the speed of light. However, the detection of tachyonic neutrinos, which would surpass that speed, poses unique challenges. One potential approach could involve observing the effects of tachyonic neutrinos indirectly, much like how dark matter and dark energy are detected by their gravitational influences rather than direct observation. Since tachyonic neutrinos would be moving faster than light, they could potentially create detectable distortions in the space-time fabric, similar to the way gravitational waves have been observed. These distortions might provide the first real evidence of their existence, offering clues about the properties and behavior of these hypothetical particles. Another approach could involve the development of new particle detectors that are specifically tuned to detect faster-than-light particles. This would require an entirely new class of instruments, potentially based on principles that are not yet fully understood. For instance, scientists could experiment with quantum technologies to measure the unique interactions of tachyonic neutrinos with other particles. Quantum computing, with its ability to handle complex calculations and simulations, could also play a pivotal role in understanding how tachyonic neutrinos might behave under various conditions. Theoretical models would also need to be developed to account for the behavior of tachyonic neutrinos. The standard model of particle physics, which has been the foundation of our understanding of particle interactions, would need to be extended or even replaced with a new framework capable of incorporating particles that move faster than light. This would require revisions to our understanding of space-time, quantum mechanics, and possibly even the fundamental forces of nature. This theoretical leap could have profound implications for other areas of physics. For example, the discovery of tachyonic neutrinos might lead to a new understanding of the forces that govern the universe at the most fundamental level. Could these particles be linked to the elusive theory of everything, a unified framework that combines general relativity and quantum mechanics? The search for such a theory has long been one of the most elusive goals of theoretical physics, and the discovery of faster-than-light neutrinos might provide the key to unlocking this puzzle. However, as exciting as the potential for discovering tachyonic neutrinos is, there are numerous challenges and obstacles that stand in the way. The first is the sheer difficulty of detecting particles that travel faster than light. Even the most sophisticated detectors may not be able to capture these elusive particles in real time, requiring scientists to develop new methodologies and technologies that can overcome the limitations of current tools. Another challenge lies in the theoretical modeling of tachyonic neutrinos. While scientists have speculated about the existence of faster-than-light particles for decades, there has been no experimental confirmation to date. Theoretical physicists would need to develop models that not only account for the existence of such particles, but also explain how they could interact with the rest of the universe. This could involve revising our understanding of quantum field theory, which forms the basis for much of modern physics. Furthermore, the potential consequences of discovering tachyonic neutrinos are still unknown. As discussed earlier, the violation of causality could lead to paradoxes and disruptions in the fundamental laws of nature. It is unclear how the universe would behave if causality were no longer a strict rule. Could this lead to instabilities in the fabric of reality, or would it open up entirely new realms of possibility? Scientists will need to carefully consider the implications of any discovery before taking the next steps in exploring this phenomenon. If tachyonic neutrinos were to be detected, the implications for our understanding of the universe would be staggering. It would mark a paradigm shift in physics, one that could alter the course of scientific inquiry for generations to come. New theories and new technologies would emerge, paving the way for a deeper understanding of the fundamental forces that shape the cosmos. We might even witness a technological renaissance, where the ability to manipulate space-time and communicate faster than light becomes a reality. The discovery of tachyonic neutrinos could also have profound effects on our understanding of the universe's origins. If these particles were present during the Big Bang, as some theorists suggest, they could hold the key to understanding the early moments of the universe. This could provide answers to some of the most profound questions in cosmology, such as why the universe is expanding at an accelerating rate, and what the true nature of dark matter and dark energy is. The role of tachyonic neutrinos in the context of cosmology cannot be overstated. If these particles are linked to the forces that drive cosmic inflation, they may help explain why the universe grew so rapidly in the first few moments after the Big Bang. Tachyonic neutrinos could be part of the unseen forces that shape the structure of the universe, influencing the distribution of galaxies and the formation of large-scale cosmic structures. Moreover, their potential connection to dark matter and dark energy could provide insight into the mysteries that have puzzled cosmologists for decades. These two phenomena make up the majority of the universe's mass, yet their properties remain a mystery. If tachyonic neutrinos are indeed related to dark matter or dark energy, their study could unlock the answers to questions that have been at the forefront of scientific inquiry for years. Another exciting possibility is the impact that tachyonic neutrinos could have on the future of space exploration. If we could harness the properties of these particles, we might be able to develop new propulsion systems that allow spacecraft to travel at faster than light speeds. This could revolutionize our ability to explore the cosmos, enabling missions to distant stars and galaxies that would have been unimaginable with current technology. However, as with any new discovery, there will be challenges and risks. The manipulation of faster-than-light particles may have unforeseen consequences, and scientists will need to exercise caution when exploring their potential applications. We must consider the long-term effects of such powerful technologies on both the universe and humanity. Tachyonic neutrinos represent one of the most intriguing and potentially transformative concepts in modern physics. Their existence would challenge our current understanding of space-time, causality, and the fundamental forces of the universe. The pursuit of these mysterious particles could lead to groundbreaking discoveries, both theoretical and practical, that reshape our understanding of the cosmos and the laws that govern it. As we continue to search for tachyonic neutrinos and explore their potential implications, we are reminded of the boundless curiosity that drives scientific progress and the limitless possibilities that lie ahead in our quest to understand the universe. The implications of discovering tachyonic neutrinos extend far beyond the realms of physics and cosmology. Their existence could provide the foundation for a new era of scientific exploration, reshaping the way we understand not just the universe, but also the very laws of nature that govern reality. As humanity progresses, the study of faster-than-light particles could redefine the limits of what is possible, both in the lab and in our day-to-day lives. The question remains, what exactly would it mean for us, as a species, to comprehend a universe that operates on principles so radically different from what we have known so far? In the practical realm, if tachyonic neutrinos could be harnessed, the consequences for technology could be extraordinary. In much the same way that understanding the behavior of electromagnetic waves led to the development of radio, television, and modern telecommunications, grasping the properties of tachyonic neutrinos could yield new breakthroughs. Imagine a world where faster-than-light travel is no longer confined to the realms of science fiction but is an actual possibility. The very concept of space exploration would be transformed. Instead of the decades-long voyages that we are currently limited to, astronauts could theoretically travel across the stars in a fraction of the time. However, to achieve such feats, scientists would need to first solve a fundamental question: how do we control and direct tachyonic neutrinos? Currently, the laws of physics as we understand them don't provide a straightforward way to manipulate particles that exceed the speed of light. As we know, faster-than-light travel presents its own set of paradoxes. The introduction of tachyonic neutrinos into our understanding of particle physics would require a complete rethinking of our ideas about space, time, and motion. Perhaps even more fundamentally, the potential discovery of tachyonic neutrinos would challenge our conceptualization of causality. According to Einstein's theory of relativity, nothing can travel faster than light without violating causality, the principle that an effect cannot occur before its cause. If tachyonic neutrinos were found to exist, this would suggest that the universe may not operate in the way we thought, allowing for events to unfold in ways that defy our understanding of time and sequence. The speed of light is the ultimate speed limit in the current framework of physics, but if tachyonic particles can exceed this limit, they would open the door to fundamentally new ways of thinking about the nature of reality itself. One possibility, as some theoretical physicists have proposed, is that tachyonic neutrinos could eventually lead to the discovery of quantum time travel. This concept suggests that particles that can exceed the speed of light might be able to travel backward in time, potentially allowing for cause and effect relationships to be violated. If this sounds like something straight out of a science fiction movie, it's because many of the ideas surrounding tachyonic particles align with the speculative realms of future technology. However, in physics, science fiction often acts as a precursor to eventual scientific breakthroughs. Time travel, while still theoretical, has been examined in depth by physicists, with concepts like wormholes and time loops proposing ways that time itself might be bent or altered. Beyond time travel, the study of tachyonic neutrinos could have far-reaching implications for the understanding of quantum mechanics. Quantum theory deals with the behavior of subatomic particles, and its foundational principles have already been shown to be vastly different from our everyday experience of the world. The discovery of particles that exist in a state where they defy the usual limits of space and time might help physicists develop a deeper understanding of how quantum systems behave on both large and small scales. Such a breakthrough could yield new insights into the very fabric of reality, shedding light on questions that have baffled scientists for centuries. Yet, the pursuit of tachyonic neutrinos is not just about advancing theoretical knowledge. The technology required to detect, measure, and potentially manipulate faster-than-light particles would no doubt lead to advancements in other scientific fields as well. Just as the race to understand atomic energy led to the development of nuclear power, the search for tachyonic neutrinos could lead to entirely new ways of generating energy. Could tachyonic neutrinos be a source of power? This idea is speculative, but the very act of studying such particles could push the boundaries of our understanding of energy production and usage. As new discoveries are made, new technologies are born. However, such revolutionary progress also comes with its own set of challenges and potential dangers. The rapid advancement of technologies that could manipulate space-time or create new forms of energy could have unforeseen consequences. We have seen throughout history that technological advancements often outpace our ability to fully understand their implications. The harnessing of atomic energy, for example, has had both positive and negative consequences. While it has provided the world with a new source of power, it has also created new risks and threats, such as nuclear proliferation and the environmental hazards of radioactive waste. The discovery and use of tachyonic neutrinos would likely require rigorous ethical considerations. If these particles could be harnessed to create faster-than-light travel, for example, what kind of global regulation would be required to manage this technology? Moreover, the philosophical implications of studying faster-than-light particles are just as profound. If we can prove that particles can exceed the speed of light, it would not only challenge the current scientific paradigm but also force us to confront deep questions about the nature of existence itself. Are the fundamental laws of the universe absolute, or are they simply a human construct that we've developed to describe the world around us? The discovery of tachyonic neutrinos could force us to reconsider the very nature of time, space, and reality itself. In addition, the potential for tachyonic neutrinos to exist alongside dark matter and dark energy raises even more intriguing possibilities. Dark matter, which makes up about 27% of the universe's mass, and dark energy, which constitutes about 68%, are still poorly understood. If tachyonic neutrinos are somehow connected to these mysterious components of the universe, they could be the missing link that allows us to better understand the fundamental structure of the cosmos. As we continue to study the universe at its most basic level, our ability to perceive the world around us will evolve in ways we can't yet predict. Just as the discovery of the Higgs boson in 2012 revolutionized our understanding of particle physics, the detection of tachyonic neutrinos could revolutionize the way we think about space, time, and the very fabric of the cosmos. The search for these particles is not just about finding new knowledge, it's about redefining the boundaries of what we know and ultimately reshaping our understanding of the universe. The potential discovery of tachyonic neutrinos would revolutionize how we perceive not just physics, but also the entire structure of the cosmos. Imagine a world where the very rules that have governed scientific understanding for centuries were suddenly called into question. If tachyonic neutrinos exist, and if they can be observed and measured, we could find ourselves at the cusp of an era in which the limitations of physics as we know them are redefined, potentially opening up entirely new fields of scientific inquiry. The ripple effects would extend far beyond the theoretical realm, bringing with them groundbreaking advancements in technology and perhaps even completely new technologies that could transform society. Consider the profound implications of faster-than-light communication. If neutrinos, or particles of a similar nature, could be manipulated, it may open the door to technologies that bypass the conventional limitations of speed, allowing information to travel instantly across vast distances. While it might sound like something out of a science fiction novel, the reality is that this would be a game-changer for global communications, pushing humanity into an era of instantaneous data transfer. There is also the potential for what could be considered tachyonic engines, devices capable of exploiting the energy or properties of tachyonic neutrinos in a way that enables near-instantaneous travel across vast distances. Imagine a spacecraft that could travel not at the speed of light, but far beyond it. Such a development would be a dream for space exploration, dramatically reducing the time it would take to reach distant stars and planets. This kind of technology could open up the possibility for humanity to explore and colonize other parts of the galaxy in ways that were once thought to be impossible. On a more practical level, the study of tachyonic neutrinos could also provide answers to some of the deepest mysteries of the universe, particularly in the realm of cosmology. The nature of dark matter and dark energy remains one of the biggest unsolved puzzles in modern science. Some theorists have speculated that the discovery of tachyonic neutrinos could help explain these enigmatic forces. If these particles interact with dark matter or dark energy in ways that we have yet to fully understand, it could shed light on how these components of the universe work and why they behave the way they do. Even the most basic questions about the universe, how it began, how it will end, and what its fundamental nature is, could be radically changed by the discovery of tachyonic neutrinos. By challenging the very fabric of our understanding of space and time, these particles could offer new insights into the early universe, potentially even providing clues to the nature of the Big Bang itself. If tachyonic neutrinos were present in the early universe, they might help us better understand the forces at play during the formation of galaxies, stars, and other cosmic structures. One of the most exciting aspects of tachyonic neutrinos is the potential for new discoveries in fundamental physics. The introduction of faster-than-light particles into the field of particle physics would undoubtedly lead to new areas of research. For example, the interaction between tachyonic neutrinos and other subatomic particles might reveal entirely new forces or forms of matter that were previously unknown. It could lead to the development of a new branch of physics that transcends our current understanding of the Standard Model and quantum mechanics. However, the road to understanding tachyonic neutrinos is not without its obstacles. As of now, there is no definitive proof of their existence, and they remain a theoretical concept. The detection of particles that travel faster than light would require extremely advanced technology, possibly beyond what is currently available. While certain experiments, such as those involving high-energy particle collisions, may provide indirect evidence of tachyonic neutrinos, direct detection is still a distant goal. Moreover, the implications of tachyonic neutrinos would likely provoke a shift in the very foundations of modern physics. If these particles exist, it could force scientists to reconsider well-established concepts such as relativity and quantum mechanics. These two theories have formed the bedrock of our understanding of the universe for over a century, and any discovery that challenges or overturns them would necessitate a complete re-evaluation of what we think we know about the fundamental forces of nature. As with any breakthrough in science, the discovery of tachyonic neutrinos would likely spark a new wave of controversy and debate. Some physicists may reject the notion entirely, arguing that the fundamental principles of relativity and causality cannot be violated. Others may embrace the discovery, seeing it as the next step in the ongoing quest to understand the universe. The debate could lead to new theoretical models that attempt to reconcile the existence of tachyonic neutrinos with the existing laws of physics. In a broader sense, the discovery of tachyonic neutrinos could have profound philosophical implications. For centuries, humanity has grappled with the idea of time and space as fixed and immutable. The notion that particles could travel faster than light, or even move backward in time, would force us to rethink our very understanding of the universe. What would it mean for causality to be violated? How would our perception of time, history, and reality itself change? These are questions that go far beyond the realm of physics and touch upon some of the deepest mysteries of existence. As scientists continue their search for tachyonic neutrinos, they are likely to encounter new challenges and questions that we have yet to even consider. The nature of these particles, if they exist, could reshape the boundaries of human knowledge and spark a new era of exploration and discovery. From fundamental physics to practical applications in technology, the discovery of tachyonic neutrinos would mark a turning point in our understanding of the universe and the laws that govern it. In the future, the study of tachyonic neutrinos could lead to technologies and theories that we can't yet imagine. As with many great scientific advancements, the full impact of such a discovery may only become clear in hindsight. Just as the discovery of quantum mechanics and relativity changed the course of physics in the 20th century, the study of tachyonic neutrinos could redefine the course of science in the coming century. The implications of such a breakthrough are profound, and as we look toward the future, we can only wonder how these enigmatic particles will shape the future of human knowledge, technology, and our understanding of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.